groundbreaking reports arrive from the frontier of our solar system. 3I Atlas has ceased behaving like an ordinary comet. Just days ago, astronomers observed this interstellar traveler pass within 2 astronomical units of the Sun, beginning to shine with intensity far exceeding all forecasts. Its gaseous envelope has expanded to dimensions rivaling half our star's diameter. Its luminosity has transformed into a disturbing green hue. Most peculiarly, it has generated a tail oriented directly toward the Sun, a phenomenon that defies physical possibility. As it hurtles toward Mars with tremendous velocity, scientists acknowledge their inability to comprehend what unfolds before them. The approach to perihelion has commenced. With each hour that passes, this extraterrestrial wanderer appears less like a comet and increasingly like a celestial mystery demanding resolution. Remain with us through tonight's investigation to discover what this developing situation reveals about everything we believed we understood, and what transpires when alien chemical processes finally emerge from dormancy. The observational data provides irrefutable evidence, even when it contradicts expectations. During mid-September 2025, astronomers tracking 3I Atlas detected something deeply concerning within their measurements. The luminosity readings began ascending beyond the anticipated trajectories, escalating from the expected magnitude range of 15 to 16 up to a remarkable 12 to 14. For those not versed in the counterintuitive system of astronomical magnitudes, this signifies a profound transformation. Consider it in these terms. Magnitude values operate inversely. Lower numerical values indicate greater brightness. A decrease of merely 2 magnitudes signifies the object now emits 6 times the predicted illumination. This wasn't a progressive transition. This represented acceleration. The Comet Observation Database, abbreviated as COBS among those who monitor these celestial travelers, began displaying data entries that climbed progressively above the standard ascending curve anticipated for a warming comet. Sky tracking observations from Earth validated the pattern. 3I Atlas was outperforming every computational model astronomers had developed for its solar approach. The pivotal moment arrived as the object penetrated inside approximately 2 astronomical units of the Sun during early to mid-September. For reference, 1 astronomical unit equals the separation between Earth and our star, approximately 93 million miles. At 2 astronomical units, 3I Atlas remained twice as distant from the Sun as our planet. Nevertheless, something fundamental shifted. The luminosity acceleration wasn't merely unanticipated. It proved alarming in its magnitude. What mechanism could trigger such a dramatic increase in brightness? The most probable explanation involves volatile frozen compounds, solidified carbon dioxide, water, and unusual materials trapped within the nucleus since the object's formation around a distant star. As solar radiation grows more intense, these substances don't simply melt. They undergo explosive transition from solid directly to gaseous state, transporting dust and fragments in expanding clouds that reflect sunlight back toward Earth. Here's what should generate concern among us. Sudden brightening episodes frequently indicate structural instability. Comets undergoing rapid outgassing can disintegrate, producing multiple fragments or spectacular debris formations. They can also deplete their volatile inventories rapidly, resulting in equally swift dimming. The observation that 3I Atlas brightens faster than models forecast suggests we're witnessing mechanisms that astronomers haven't completely comprehended. This doesn't warrant global alarm. NASA has verified that 3I Atlas maintains secure separation, never approaching nearer than 1.8 astronomical units to Earth, almost double the distance to our Sun's location. The concern isn't regarding impact. It's regarding understanding. We may be observing an interstellar archive undergoing fundamental alterations in real time. As it plunges toward the inner solar system, reflect upon the ramifications. This object originated in the debris disk surrounding another star, perhaps hundreds of light years distant. It coalesced from materials that never experienced our sun's thermal energy, never encountered the particular conditions that molded the bodies indigenous to our cosmic region. Yet presently, for the initial time in its existence, it's experiencing the concentrated radiation environment of our inner solar system. The brightness surge could represent the activation of chemistry that has remained inactive for millions or billions of years. Exotic frozen compounds, stable in the frigid vastness of interstellar space, might now be sublimating for the inaugural time since the object's formation. We're potentially witnessing the revelation of chemical indicators from another stellar system, preserved in immaculate condition across the galaxy. The chronology creates supplementary urgency. 3I Atlas is approaching a sequence of critical dates that will determine what astronomers can extract from this exceptional visitor. October 3rd designates its nearest approach to Mars, a mere 30 million kilometers, sufficiently close for spacecraft orbiting the red planet to potentially observe details imperceptible from Earth. By late October, specifically October 29th to 30th, the comet achieves perihelion, its closest approach to the Sun, at approximately 1.36 to 1.4 astronomical units. Here's where the narrative takes a problematic direction for Earth-based observers. As 3I Atlas nears its encounter with our star, its celestial position advances perilously close to the Sun's overpowering radiance. From early October through early November, the comet enters what astronomers designate superior conjunction, a duration when the Sun's brilliance renders observation virtually impossible from Earth's surface. This signifies the maximum activity of our interstellar visitor, the instant when solar heating achieves its peak intensity and the comet's authentic nature might be unveiled, will transpire largely concealed from our view. We'll be compelled to depend on the mechanical sensors of spacecraft distributed throughout the solar system, particularly those orbiting Mars, to witness what could be the most magnificent exhibition of interstellar chemistry in recorded history. The brightening pattern suggests 3I Atlas won't pass quietly through perihelion. Present observations indicate an object energized by its encounter with our Sun, possibly developing toward explosive episodes that could illuminate previously invisible aspects of its structure and composition. But will these discoveries occur during the weeks when Earth's telescopes are obscured by solar brilliance? The information emerging from September's observations portrays an object in metamorphosis. The recorded brightness coordinates trending above anticipated curves indicate that 3I Atlas is transforming into something distinct from what it was during its extended journey through interstellar space. The question remains whether this transformation represents normal cometary behavior in an exotic object or something completely unprecedented in our experience with visitors from other stellar systems. In the forthcoming segments, we'll investigate why this object's coma extends beyond what should be physically possible, why its tail orients toward the Sun rather than away from it, and how its recent transition to an unsettling green luminescence might signal chemical processes never before documented in an interstellar visitor. The enigmas are multiplying as rapidly as the brightness measurements are ascending. But initially, we need to comprehend what we're examining, because 3I Atlas isn't simply any comet. It's only the third confirmed visitor from another stellar system, and its behavior is already demonstrating that each interstellar object carries its own governing principles. The chronicle of 3I Atlas originates on a mountaintop in Chile, where robotic instruments scan the nocturnal sky with mechanical precision that surpasses human observation capabilities. On July 1st, 2025, the asteroid terrestrial impact last alert system, abbreviated as ATLAS, detected a faint blur of illumination moving against the stellar backdrop. Initially recorded as merely another minor celestial body, this unremarkable observation would shortly revolutionize our comprehension of interstellar visitors. What designates an object as interstellar isn't solely its origin beyond our solar system. It's the mathematical certainty that it can never be gravitationally captured by our sun's orbit. 3I Atlas follows what astronomers term a hyperbolic trajectory, a path so energetic that once it completes its arc around our star, it will continue outward eternally, never to return. The orbital calculations are unforgiving in their accuracy. This object possesses excessive velocity to be captured by our sun's gravitational field. The 3I designation conveys its own narrative. The I represents interstellar, while the numeral 3 indicates this is only the third such object confirmed in human history. Its predecessors, 1I Oumuamua in 2017 and 2I Borisov in 2019, each astonished astronomers with distinctive characteristics that resisted simple categorization. Now 3I Atlas perpetuates this pattern of interstellar unpredictability. The discovery methodology reveals precisely how challenging these objects are to detect. Atlas operates from the Rio Hurtado Observatory in Chile's Atacama Desert, component of a worldwide network engineered to identify potentially dangerous asteroids approaching Earth. The system captures multiple exposures of identical sky regions over brief time intervals, then employs computer algorithms to recognize anything that shifts against the stellar background. On that July evening, 3I Atlas manifested as little more than a faint streak, barely distinguishable from the thousands of asteroids, comets, and space debris that populate our inner solar system. However, recovery images earlier photographs that display the object, prior to its official discovery disclosed, that 3I Atlas had been present in astronomical databases for weeks before anyone acknowledged its significance. This delayed recognition is typical with interstellar objects, which frequently appear asteroid-like. In initial observations before developing the diffuse comas and tails that identify them as comet-like bodies, the preliminary assessment revealed a faint coma enveloping the central nucleus, immediately suggesting that 3I Atlas was more than merely a rocky asteroid. Comets develop these fuzzy atmospheres when solar heating causes ices to sublimate, generating expanding shells of gas and dust. The presence of a coma at such distance from the Sun 3I Atlas was still beyond 3 astronomical units when discovered indicated that this object contained volatile materials capable of outgassing even in the frigid outer regions of our solar system. As news of the discovery circulated through the astronomical community, larger telescopes began orienting toward this new interstellar visitor. The Hubble Space Telescope captured comprehensive images in July, while the Very Large Telescope in Chile and other ground-based observatories contributed their own observations. These follow-up investigations revealed an object far more intricate than its initial discovery images had implied. Size calculations for 3I Atlas remain frustratingly imprecise, a common challenge when studying objects too distant and faint for direct measurement. Hubble's August update refined the possibilities to a nucleus somewhere between 0.32 and 5.6 kilometers in diameter, a range that reflects the difficulty of separating the solid nucleus from its surrounding coma. The size uncertainty matters because it affects calculations of the object's mass, density, and structural stability as it approaches the sun's intense heating. Velocity calculations paint a clearer portrait of this object's extraordinary nature. Currently racing through space at approximately 130,000 miles per hour, roughly 58 kilometers per second. 3 Atlas moves at velocities that dwarf anything naturally occurring in our solar system. For comparison, Earth orbits the Sun at a sedate 30 kilometers per second. The comet's speed will continue escalating as solar gravity accelerates it toward perihelion, potentially reaching 68 kilometers per second or more than 150,000 miles per hour. These velocities underscore the alien nature of our visitor. No object born in our solar system could naturally achieve such speeds without assistance from gravitational slingshot maneuvers around massive planets. 3I Atlas carries the kinetic signature of its interstellar origin, accumulated during millions of years of travel through the galaxy. Under the influence of stellar gravitational fields and galactic rotation, the rarity of confirmed interstellar visitors renders each one invaluable to science. Before 2017, astronomers possessed only theoretical models to guide their understanding of how objects might behave during interstellar journeys. 1I Oumuamua shattered many assumptions with its elongated shape and mysterious non-gravitational acceleration. 2I Borisov appeared more conventionally comet-like, but revealed chemical compositions unlike anything in our solar system. Now 3I Atlas adds a third data point to this sparse collection, and early indications suggest it will prove as unique as its predecessors. The object's behavior challenges models in novel ways, particularly its unexpectedly large coma and unusual brightness evolution. Each interstellar visitor seems to carry its own set of physical and chemical principles, suggesting that the galaxy harbors far more diversity in small body formation processes than we previously conceived. The classification process involves more than simply confirming interstellar status. Astronomers must also determine whether 3I Atlas represents an asteroid-like body, a comet, or something entirely different. The presence of a coma strongly suggests comet-like behavior, but the specific gases and dust compositions revealed through spectroscopic analysis will ultimately determine how this object formed and evolved in its birth star system. This is not a local comet expelled inward from the Oort cloud, that distant reservoir of icy bodies that occasionally sends visitors toward the inner solar system. 3I Atlas formed around another star, condensed from materials that experience different temperatures, pressures, and chemical environments than anything indigenous to our cosmic neighborhood. It represents a direct sample of planetary formation processes that occurred light years away, possibly billions of years ago. The trajectory calculations position 3I Atlas on a path that will provide unprecedented observation opportunities, particularly during its close approach to Mars on October 3rd. This geometry isn't accidental. The object's orbital inclination and timing align favorably for spacecraft observations precisely when Earth-based telescopes will lose sight of it due to solar glare. But understanding what we're observing requires more than simply knowing where 3I Atlas originated and where it's traveling. The genuine mysteries lie in how it's behaving as it encounters our sun's radiation for the initial time in its existence, and why that behavior differs so dramatically from theoretical predictions. Time is diminishing for 3I Atlas, and for the astronomers racing to understand it before it vanishes into solar glare. The mathematics of orbital mechanics have drawn a precise roadmap through the inner solar system, marking critical dates that will determine what humanity can learn from our third confirmed interstellar visitor. October 3rd, 2025 represents the first crucial milestone. On this date, 3I Atlas will sweep past Mars at a distance of approximately 30 million kilometers, roughly 0.19 to 0.2 astronomical units. In cosmic terms, this constitutes an extremely close encounter, positioning the interstellar visitor well within the operational range of multiple spacecraft currently orbiting the red planet dot. The timing couldn't be more fortuitous or more frustrating. Just as 3I Atlas reaches its closest approach to Mars, offering spacecraft the clearest possible view of an interstellar object in action, Earth-based telescopes begin losing their ability to track it. The cruel geometry of orbital mechanics positions the comet increasingly close to the sun's location in our sky. creating observational challenges that will soon become insurmountable. By late October, specifically October 29th to 30th, 3I Atlas reaches perihelion, its closest approach to the Sun, at approximately 1.36 to 1.4 astronomical units. This distance positions it just inside Mars's average orbital radius, subjecting the interstellar visitor to solar radiation intensities unlike anything it experienced during its journey through the galaxy. The timing coincides almost perfectly with the period of greatest observational difficulty from Earth. The velocity evolution tells its own dramatic narrative. Currently traveling at tens of kilometers per second, 3I Atlas will reach its maximum velocity near perihelion, potentially hitting 68 kilometers per second, or approximately 152,000 miles per hour. To contextualize this, Earth maintains its stable orbit around the Sun at roughly 30 kilometers per second. 3I Atlas will be moving more than twice as fast as our entire planet. These velocities represent more than impressive statistics. They reveal the fundamental physics governing interstellar motion. Unlike objects indigenous to our solar system, which gained their speeds through gravitational interactions with the Sun and planets over billions of years, 3I Atlas carries kinetic energy accumulated during its journey between star systems. Every kilometer per second of velocity represents vast distances traveled through interstellar space, influenced by the gravitational fields of multiple stars and the rotation of the galaxy itself. The approach trajectory positions 3I Atlas near the ecliptic plane, the relatively flat disk containing most planetary orbits. This geometry facilitates the close encounter with Mars and will later enable a distant approach to Jupiter in 2026. The orbital alignment isn't coincidental. Objects approaching from random directions in three-dimensional space would be unlikely to pass so conveniently close to multiple planets during their brief transit through our solar system. Safety considerations never entered the equation for 3I Atlas. Despite its classification as a potentially hazardous object during initial tracking, the closest approach to Earth occurs at approximately 1.8 astronomical units, nearly twice the distance to the Sun, and well beyond any conceivable threat. NASA's confirmation of this safe distance eliminated public concern about collision, allowing astronomers to focus on the scientific opportunities rather than planetary defense considerations. The genuine challenge lies in observational geometry. From early October through early November, 3I Atlas experiences what astronomers call superior conjunction, a period when its position in Earth's sky places it too close to the Sun for practical observation. Solar elongation, the angular separation between the comet and Sun as seen from Earth, drops below 30 degrees for much of this critical period. Imagine attempting to spot a firefly hovering next to a floodlight, and you begin to understand the observational predicament. Even the most sophisticated telescopes cannot separate the faint illumination of 3I Atlas from the overwhelming glare of our star when the two objects appear close together in the sky. This natural limitation of Earth-based astronomy means that the comet's most active period may occur largely hidden from human observation. The conjunction timing creates a fundamental irony in the 3I Atlas encounter. Just as solar heating reaches its maximum intensity and the comet potentially undergoes its most dramatic transformations, Earth's astronomical community will be effectively blinded. The peak outgassing, possible fragmentation events, and maximum tail development could all occur during the weeks when ground-based telescopes cannot function effectively. This observational gap places extraordinary importance on spacecraft positioned throughout the solar system, particularly those orbiting Mars. The European Space Agency's Mars Express and Trace Gas Orbiter, along with NASA's Mars Reconnaissance Orbiter and MAVEN, suddenly find themselves in the role of humanity's primary eyes on one of the most significant astronomical events of the decade. The post-perihelion timeline offers both optimism and realism about what observers can expect. Assuming 3I Atlas survives its solar encounter intact, Earth-based observations should resume in November or early December as solar elongation increases beyond practical limits. However, the comet will likely be fading rapidly by then, having exhausted much of its volatile content during the unobserved peak heating period. Magnitude predictions suggest that even at its brightest, 3I Atlas will remain a telescopic object for Earth-based observers. Peak brightness estimates hover around magnitude 11 to 12, far too faint for naked eye visibility, but well within the range of amateur astronomical equipment. The absence of a spectacular naked eye display may disappoint casual observers, but it doesn't diminish the scientific value of this unprecedented interstellar encounter. The velocity profile reveals another crucial aspect of the 3I Atlas timeline. As the object approaches perihelion, its speed continues increasing under solar gravitational acceleration. However, immediately after closest approach, that same gravity begins decelerating the comet as it moves away from the sun's location. This velocity change affects the duration of peak heating and the time frame available for observation by Mars-based spacecraft. Looking beyond perihelion, the trajectory calculations show 3I Atlas continuing outward through the solar system, eventually approaching Jupiter in March 2026. While this encounter will occur at a much greater distance than the Mars flyby, it may provide additional opportunities for spacecraft observations as the comet begins its final exit from our solar system. The timeline creates a narrow window of opportunity that astronomy has never faced before. Unlike periodic comets that return regularly, allowing multiple opportunities for study, 3I Atlas offers a single chance to understand an object from another star system. The observational challenges, conjunction timing, and spacecraft opportunities must all align perfectly for humanity to extract maximum scientific value from this cosmic visitor. As we approach the critical October dates, the question isn't just what 3I Atlas will reveal about itself, but whether our observational capabilities will prove adequate to capture those revelations. The mathematics of orbital mechanics have set the schedule, and that schedule waits for no one. The most astonishing discovery about 3I Atlas isn't its interstellar origin or unusual trajectory. It's the sheer impossible scale of the atmosphere it's creating around itself. In September 2025, NASA's SpareX telescope detected something that defied every model astronomers had constructed for comet behavior: an extended carbon dioxide coma stretching 348,000 kilometers from the nucleus. To grasp the magnitude of this measurement, consider that this ghostly atmosphere extends roughly half the diameter of our Sun. The coma of 3I Atlas has grown large enough to contain Mercury's entire orbit, creating a bubble of gas and dust that dwarfs anything typically observed around comets in our solar system. This isn't just unusual, it's unprecedented in the annals of cometary science. Coma forms when solar radiation heats the ices locked within a comet's nucleus, causing them to sublimate directly from solid to gas without passing through a liquid phase. Think of it as a cosmic snowball steaming in sunlight. But the analogy fails to capture the violence of the process. As frozen materials explosively transition to gas, they carry dust particles and larger debris outward, creating an expanding atmosphere that can grow to enormous proportions. The composition of 3I Atlas's coma tells a story of formation in conditions radically different from our solar system. The dominance of carbon dioxide over water vapor suggests this object condensed in a region where CO2 could freeze out more readily than H2O, possibly in the outer reaches of another star's planetary disk, where temperatures remained low enough for carbon dioxide ice to remain stable while water existed primarily as vapor. This CO2-rich environment hints at the chemical conditions present during 3I Atlas's birth. Most comets in our solar system show water as their primary volatile component, with carbon dioxide playing a secondary role. The reversed ratio observed in 3I Atlas indicates formation temperatures and pressures, unlike anything experienced by objects native to our cosmic neighborhood. But the coma's composition isn't its only unusual characteristic. Images from the Hubble Space Telescope and ground-based observatories reveal structure that challenges fundamental assumptions about comet behavior. Instead of the classic tail streaming away from the sun, 3I Atlas displays what astronomers call an anti-tail, a plume of material that appears to point sunward. This sunward-pointing structure represents a puzzle that has kept researchers working through sleepless nights. Conventional comet physics dictates that solar radiation pressure should push gas and dust away from the sun, creating the familiar tales that have inspired human imagination for millennia. Yet 3I Atlas seems to be violating this basic principle, ejecting material in directions that contradict textbook explanations. Hubble's July 21st observations captured what mission scientists described as a forward glow, a fan-shaped structure extending from the nucleus toward the sun rather than away from it. Follow-up imaging by the Gemini South Telescope on August 27th showed this unusual geometry persisting and evolving, suggesting that the anti-tail represents a stable feature rather than a temporary anomaly. The physics behind anti-tail formation involve processes more complex than simple radiation pressure. Large dust grains, too massive to be easily pushed by solar photons, can maintain sunward trajectories if they're ejected from the nucleus with sufficient initial velocity. Additionally, projection effects can make material moving in three-dimensional space appear to point toward the sun when viewed from Earth's specific vantage point. However, theoretical models struggle to explain the persistence and prominence of 3I Atlas's sunward plume. The structure appears too well-defined and long-lasting to result from simple projection effects, while the required dust grain sizes and ejection velocities needed to create such an extensive anti-tail push the boundaries of what's physically reasonable for a comet nucleus. Recent analysis suggests that the anti-tail might result from unusual rotation states or surface properties unique to interstellar objects. A slowly spinning nucleus could maintain temperature differences between its day and night sides that concentrate outgassing in specific directions. Alternatively, the surface composition of 3I Atlas might include materials that respond to solar heating in ways unfamiliar to researchers accustomed to studying local comets. The coma's expansion rate adds another layer to the mystery. Spectroscopic observations indicate that gas velocities within the coma exceed typical values for comets at similar distances from the sun's location. This enhanced outgassing could result from the release of supervolatile compounds that remain stable only in interstellar conditions, sublimating rapidly when first exposed to significant solar heating. Temperature measurements of the coma reveal additional anomalies. The gas temperatures recorded by infrared observations suggest heating mechanisms beyond simple solar absorption. Possible explanations include chemical reactions between previously separated compounds, or the release of energy stored in exotic ice crystal structures that formed under interstellar conditions. The three-dimensional structure of the coma, reconstructed from multiple viewing angles and different wavelengths of light, shows asymmetries that point to non-uniform outgassing from the nuclear surface, rather than the relatively symmetric comas typical of well-studied comets. 3I Atlas displays jets and fans of material emerging from specific regions of its nucleus. These jets suggest that the nuclear surface contains discrete areas of volatile rich material, possibly exposed by impacts or thermal cycling during the object's interstellar journey. The pattern of outgassing could preserve information about the comet's formation environment and subsequent evolution during millions of years of travel through space. Dust analysis within the coma reveals particle size distributions unlike those found in solar system comets. The abundance of large grains necessary to create the observed anti-tail structure suggests that 3I Atlas either formed with different dust-to-ice ratios than local comets, or that its dust particles have undergone modification. Processes during interstellar transit. The expansion dynamics show temporal variations that correlate with the comet's distance from the Sun and potentially with rotation periods. As 3I Atlas continues its approach toward perihelion, the coma continues growing and evolving, potentially reaching even larger dimensions as solar heating intensifies. Modeling efforts to predict the coma's future evolution face unprecedented challenges. The unusual composition, anti-tail geometry, and enhanced outgassing rates all require modifications to standard cometary physics models. Researchers are effectively developing new theoretical frameworks in real time as observations continue to reveal unexpected behaviors. The implications extend beyond 3I Atlas itself. If interstellar comets routinely display such unusual coma characteristics, it suggests that our understanding of comet physics, based primarily on objects native to our solar system, may represent only a narrow subset of possible behaviors. Each interstellar visitor could force revisions to fundamental assumptions about how these objects form and evolve. As 3I Atlas approaches its critical encounters with Mars and the Sun, the coma's continued expansion and structural evolution will provide crucial tests of competing theoretical models. The question is whether the most dramatic changes will occur during the observational gap when Earth's telescopes cannot track the comet's behavior, but the coma's evolution represents only one aspect of 3I Atlas's transformation as it encounters our Sun's radiation. The most visually striking change occurred in mid-September when the entire comet began glowing with an eerie green light that signaled chemistry unlike anything previously observed in an interstellar visitor. During mid-September 2025, 3I Atlas performed an action that created waves of enthusiasm throughout the astronomical community. The object shifted to green not in a gradual or subtle manner, but with an intense emerald luminescence that converted this interstellar traveler from a faint blur into something that appeared almost living against the star-saturated void. The chromatic transformation wasn't instantly apparent to everyday watchers. 3I Atlas stayed too dim for unaided eye detection. Yet sensitive imaging equipment connected to telescopes across the globe started recording photographs that revealed an undeniable green hue encircling the comet's core. The change became especially noticeable in pictures captured during the lunar eclipse on September 14th, when the moon's shadow delivered darker conditions that amplified the contrast of the comet's newly acquired radiance. The green luminescence communicates a narrative expressed in the vocabulary of quantum mechanics and molecular chemistry. When particular molecules capture ultraviolet radiation from the Sun, their electrons leap to elevated energy levels. As these electrons return to their baseline condition, they release light at precise wavelengths that our vision interprets as specific colors. In 3I Atlas's situation, the green radiation most probably comes from diatomic carbon-2 carbon atoms linked together, indicated as C2 in chemical terminology. Diatomic carbon functions like a molecular illuminated sign in the cosmos. When activated by solar ultraviolet energy, C2 molecules discharge light at wavelengths near 516 nanometers, generating the distinctive green luminescence that has rendered 3I Atlas among the most visually remarkable comets witnessed in recent times. This emission mechanism, termed fluorescence, converts invisible solar power into visible radiation that can traverse millions of kilometers to arrive at Earth-based telescopes. Yet here's where the narrative grows perplexing. Initial spectroscopic examinations of 3I Atlas revealed comparatively minimal indication of carbon-containing compounds. The preliminary chemical assessment indicated a makeup dominated by carbon dioxide and water vapor, with merely trace quantities of the carbon-rich molecules conventionally responsible for green comet coloring. This seeming paradox between the witnessed green luminescence and the measured chemical structure has scientists rushing to comprehend what's genuinely occurring in the comet's expanding envelope. 1. Potential explanation involves phase changes in the comet's outgassing patterns. As 3I Atlas traveled nearer to the Sun and passed the 2 astronomical unit boundary in early September, intensified solar warming may have initiated the sublimation of previously unreachable deposits of carbon-rich substances within the nucleus. These substances, secured within the comet's interior throughout its extended interstellar voyage, might currently be encountering solar radiation for the first instance in their existence. The scheduling of the green color transformation aligns suspiciously perfectly with the interval of rapid illumination witnessed in mid-September. This implies that the identical physical mechanisms responsible for the unexpected brightness increase potentially the catastrophic discharge of volatile substances from underground reserves also initiated the chemical reactions generating the green radiation. Alternative interpretations for the color transformation involve more intricate chemistry than elementary diatomic carbon fluorescence. Comets can harbor dozens of distinct carbon-containing molecules, each possessing its individual emission properties. The visible green luminescence might stem from a combination of emissions from numerous species, or from carbon-bearing molecules exclusive to interstellar settings that don't manifest in substantial amounts. Among solar system comets, instrument sensitivity and processing methodologies also introduce ambiguity into color determinations. Various telescopes employing different filters and imaging mechanisms can yield subtly distinct color representations of the identical object. What seems distinctly green in one photograph might appear more blue-green or yellow-green in another, depending on the particular wavelengths captured and the techniques employed to merge them into color. Photographs dot the progression of the green luminescence supplies additional evidence about the fundamental chemistry. Unlike the constant emission anticipated from simple molecular fluorescence, observations indicate that the green coloring fluctuates in strength and placement within the coma. Some areas seem more intensely green than others, suggesting that carbon-containing molecules aren't uniformly spread throughout the expanding gas formation. This non-uniform dispersion could arise from discrete outgassing incidents where streams of material erupting from particular positions on the nucleus transport different chemical makeups. Alternatively, the variation might reflect chemical transformation within the coma itself, as solar ultraviolet radiation decomposes complex organic molecules into simpler components that fluoresce at different wavelengths. The green emission additionally furnishes a diagnostic instrument for comprehending the physical circumstances within the coma. The strength of molecular fluorescence relies on the concentration of molecules, their temperature, and the intensity of solar ultraviolet radiation. By quantifying how the green luminescence differs with separation from the nucleus and evolves over time, scientists can chart the three-dimensional architecture of the carbon-containing gas within 3I Atlas's atmosphere. Temperature calculations derived from the green emission attributes suggest that the carbon-containing molecules exist in a condition of thermal balance with the remaining coma gases. This signifies efficient energy exchange between different molecular varieties, offering perspectives into collision frequencies and gas dynamics. Within the expanding envelope, manifestation of green pigmentation in 3I Atlas contributes another reference point to the expanding catalog of distinctions between interstellar Visitors and indigenous solar system objects. One-eye Oumuamua exhibited no obvious indications of cometary activity and consequently no color alterations. Two-eye Borisov displayed more traditional comet colors, dominated by blue and white scattered sunlight instead of molecular emission bands. Three-eye Atlas constitutes the first interstellar comet to develop the quintessential green coma that amateur astronomers connect with approaching periodic comets. Nevertheless, the specific wavelengths and intensity of the green emission may differ subtly from those of familiar comets, potentially disclosing chemical compositions distinctive to objects formed in alternative star systems. The timing of the color alteration generates additional observational urgency. As Three-Eye Atlas nears superior conjunction and becomes unobservable from Earth in early October, the green emission may continue transforming or could vanish entirely. The maximum intensity of molecular fluorescence frequently happens near perihelion when solar heating attains its peak. However, this crucial interval will be largely concealed from Earth-based telescopes. Spectroscopic follow-up examinations attempt to pinpoint the exact molecules accountable for the green emission. Yet these measurements demand large telescopes and advantageous observing, circumstances that become progressively difficult to secure as the comet nears the sun's brilliance. Each evening of clear conditions becomes invaluable as astronomers race to characterize the emission. Before losing view of their subject, the green luminescence transformation signifies more than merely a visually remarkable development. It furnishes direct proof that Three-Eye Atlas is experiencing fundamental chemical alterations as it encounters our sun's radiation. The molecules currently fluorescing in the comet's coma have probably remained chemically inactive for millions of years, maintained in frozen stillness during the object's journey between star systems. Now, for the first occasion since its formation, Three-Eye Atlas is literally illuminating as solar energy triggers chemical processes that have been inactive since the comet's origin around another star. The green luminescence indicates the awakening of alien chemistry, initial movements of molecular activity in materials that formed under circumstances possibly unlike anything in our solar system. Yet witnessing this awakening presents obstacles that strain the boundaries of ground-based astronomy, the obstacles that will soon compel researchers to depend on mechanical sensors positioned throughout the solar system to continue observing our transformed interstellar visitor. The universe possesses a merciless sense of timing regarding Three-Eye Atlas, precisely as this interstellar visitor starts, disclosing its most fascinating mysteries: the rapid illumination, the impossible coma, the alien green luminescence. The mechanics of orbital geometry conspire to remove it from Earth-based observers at the most vital moment of its passage. Professional telescopes fitted with the most advanced instruments humanity can construct face the identical fundamental restriction that disappoints backyard astronomers. You cannot observe what conceals behind the sun's location. As Three-Eye Atlas proceeds with its approach toward perihelion, its position in Earth's sky shifts inexorably nearer to our star's overpowering radiance, establishing observational obstacles that no quantity of technological progress can surmount. The James Webb Space Telescope succeeded in capturing spectroscopic observations of Three-Eye Atlas on August 6th using its near-infrared spectrograph, delivering essential chemical composition information during one of the limited windows when the world's most sophisticated observatory could safely aim toward the comet without endangering solar damage. These observations constitute some of the most comprehensive chemical analysis achievable for an interstellar object. Yet they transpired before the dramatic transformations of mid-September that converted Three-Eye Atlas from a merely peculiar comet into an actively bewildering one. Hubble Space telescope provided its own observations on July 21st, recording high-resolution photographs that disclosed the sunward-pointing plume configuration and supplied size limitations for the nucleus. However, since August, new high-resolution imagery from major space-based observatories has become scarce. The observatories that can deliver the detailed examination necessary to comprehend Three-Eye Atlas's unusual conduct are the same ones most susceptible to solar interference. As the comet approaches conjunction, ground-based observatories confront their own cascade of difficulties. Different telescopes utilizing different filter mechanisms and calibration protocols generate brightness measurements that don't invariably concur with each other. This discrepancy isn't unusual in astronomy brightness measurement, or photometry necessitates careful attention to atmospheric circumstances, instrument calibration, and standardization protocols that can differ between observatories. The Comet observation database endeavors to reconcile these distinctions by gathering brightness reports from observers worldwide and charting them against theoretical models. Throughout September, the COB's data unmistakably demonstrated Three-Eye Atlas trending brighter than forecasted, with measured magnitudes consistently exceeding the anticipated curve. Yet the dispersion in individual measurements mirrors the obstacles faced by observers attempting to monitor a rapidly changing object that defies their meticulously constructed models. Amateur astronomers, frequently operating with smaller telescopes and less sophisticated apparatus, contribute valuable long-term monitoring information that professional observatories cannot constantly supply. Nevertheless, their measurements encounter additional uncertainties from atmospheric turbulence, light pollution, and equipment restrictions. The outcome is a patchwork of observations that collectively depict a picture of unusual conduct, while individually containing sufficient uncertainty to stimulate debates about what's genuinely transpiring. Skilliv and other monitoring websites assemble these diverse observations into light curves that illustrate brightness evolution across time. The sites that monitor Three-Eye Atlas consistently display the same troubling pattern: measured brightness points ascending above the predicted trajectory, especially after mid-September. Yet the exact magnitude of this deviation remains uncertain due to the inherent obstacles in measuring faint, rapidly changing objects. Solar elongation, the angular separation between Three-Eye Atlas and the Sun as perceived from Earth, represents the fundamental constraint restricting all observations. As this angle diminishes below 30 degrees, even the most powerful telescopes struggle to distinguish the comet's faint light from scattered sunlight in Earth's atmosphere. Professional observatories typically halt observations when elongation falls below 20 degrees, while amateur observers may lose the object even earlier due to equipment restrictions and local observing circumstances. The elongation timeline establishes a countdown that no human technology can prolong. In early October, Three-Eye Atlas descends below the 30-degree threshold that designates the commencement of serious observational challenges. By mid-October, elongation diminishes to less than 20 degrees, effectively terminating routine observations from Earth's surface. This interval of invisibility extends through early November, encompassing the critical weeks when solar heating achieves its maximum intensity. The irony is striking. We're attempting to watch a cosmic firefly hovering beside a floodlight using instruments designed to detect the faintest whispers of light from the most remote galaxies. Even adaptive optic systems that can compensate for atmospheric turbulence and coronagraphs engineered to obstruct stellar light cannot overcome the fundamental physics of scattered sunlight when the comet appears too proximate to the Sun's position in the sky. Space-based observatories theoretically possess advantages over ground-based telescopes in managing solar interference. Yet they face their own limitations. Instruments like Hubble and James Webb incorporate protective mechanisms that prevent them from pointing too close to the sun, automatically terminating observations when solar angles become hazardous. These safety mechanisms, indispensable for preventing catastrophic damage to billion-dollar instruments, generate observation gaps precisely when they would be most beneficial. The timing of 3I Atlas's conjunction period couldn't be worse for understanding its peak activity. Theoretical models forecast that maximum outgassing, possible fragmentation incidents, and the most dramatic tail development should all transpire near perihelion in late October. These are precisely the phenomena that could disclose the most about 3I Atlas's composition, structure, and origins, and they will occur largely hidden from human observation. Data processing obstacles compound the observational difficulties. Images of 3I Atlas must be carefully processed to isolate the comet's signal from background stars, cosmic rays, and instrumental artifacts. As the object becomes fainter relative to sky brightness during its approach to conjunction, these processing stages become increasingly critical and increasingly susceptible to introducing errors or artifacts, spectroscopic observations essential for understanding the chemical composition of the comet's coma and tail require even more specialized circumstances than simple brightness measurements. The instruments needed to disperse comet light into its constituent wavelengths function best with bright targets observed under dark skies. As 3I Atlas fades into solar glare, opportunities for detailed spectroscopic examination vanish just when chemical activity may be reaching its peak. The atmospheric restrictions affect different wavelengths of light in different manners. Ultraviolet emissions, crucial for detecting many molecular species in comet comas, become particularly difficult to observe as elongation decreases because Earth's atmosphere scatters blue and ultraviolet light more efficiently than red wavelengths. This scattering effect, which gives our sky its blue color, creates additional obstacles for studying the chemical processes occurring within 3I Atlas's expanding atmosphere. Coordination between observatories becomes essential as observing conditions deteriorate. Facilities at different latitudes and in different time zones must collaborate to maximize the limited observation windows available each night. Southern Hemisphere observatories may retain better viewing geometry slightly longer than their northern counterparts, creating opportunities for extended monitoring that require careful international coordination. The photometric scatter and brightness measurements reflects more than instrumental limitations. It may also indicate real variability in 3I Atlas's output. Comets can undergo rapid changes in brightness due to outgassing events, rotation effects, or structural changes in their nuclei. Distinguishing between measurement uncertainty and genuine comet variability becomes increasingly difficult as signal-to-noise ratios decrease during the approach to conjunction. Weather adds another layer of uncertainty to ground-based observations. Cloud cover, atmospheric turbulence, and seasonal weather patterns at major observatories can eliminate crucial observation opportunities that will not recur. Unlike periodic comets that return predictably, 3I Atlas offers only a single passage through the inner solar system, making each clear, night precious, and irreplaceable. The challenge extends beyond individual observations to the broader question of how to interpret the data that does exist. The brightness trend showing 3I Atlas exceeding predicted values could indicate enhanced outgassing, structural changes, or simply systematic errors in the theoretical models used for comparison. Resolving these questions requires the kind of detailed long-term monitoring that becomes impossible as the comet disappears into solar glare. As Earth-based astronomy reaches its limits in observing 3I Atlas, the responsibility for continued monitoring shifts to mechanical sensors, positioned throughout the solar system spacecraft orbiting Mars, designed for entirely different missions, suddenly find themselves serving as humanity's primary observers of one of the most significant astronomical events of the decade. Behind the measured language of scientific papers and the carefully qualified statements in astronomical bulletins, something approaching excitement and, yes, alarm ripples through the global community of comet researchers. 3I Atlas isn't behaving according to the scripts written by decades of cometary science, and astronomers are beginning to admit, in the cautious way that scientists acknowledge uncertainty, that they might be witnessing something unprecedented. The brightness trend documented by observers worldwide represents more than statistical noise or measurement error. Multiple independent tracking systems, from the Comet Observation Database to specialized amateur networks, show the same unsettling pattern. 3I Atlas consistently outshining the predictions derived from standard cometary models. The magnitude of this deviation, several brightness levels above expected values, falls well outside the margins typically attributed to observational uncertainty. Dr. Matthew Knight, a cometary scientist who has devoted his career to studying how these objects behave, recently noted in an interview that the rapid brightening event observed in mid-September challenges fundamental assumptions about volatile release mechanisms in comets. The speed of the change, he suggested, indicates processes operating on timescales much faster than the gradual heating models typically used to predict comet behavior. This scientific uncertainty breeds a particular type of excitement among researchers, the recognition that they might be observing phenomena that will require new theoretical frameworks to understand. Earth-Sky, reporting on 3I Atlas, captures this tension, describing observations that continue to surprise researchers while acknowledging that much of what appears unusual might reflect the inherent unpredictability of objects formed in other star systems. Sunward-pointing plume structure generates its own category of scientific puzzlement. Anti-tail phenomena aren't unknown in cometary science, but the persistence and prominence of 3I Atlas's forward-directed jets push the boundaries of what existing models can easily explain. Researchers find themselves proposing increasingly exotic scenarios, unusual dust grain compositions, non-uniform nucleus rotation, exotic volatile mixtures to account for behavior that defies textbook explanations. What everyone in the field agrees on is that 3I Atlas is demonstrating enhanced activity levels compared to typical comets at similar distances from the Sun. The carbon dioxide-dominated coma detected by SPHERX, extending to unprecedented distances, suggests outgassing rates that exceed standard predictions by significant margins. This isn't subtle deviation from theory, it's dramatic departure that demands explanation. Yet, the scientific community also grapples with what researchers call outburst bias, the tendency for comets to undergo brief periods of enhanced activity that can create false impressions of sustained unusual behavior. Comets are notoriously prone to sudden brightness surges, followed by equally rapid returns to predicted levels. The question haunting 3I Atlas observations is whether the September brightening represents a genuine departure from normal behavior, or simply a temporary outburst that will fade as quickly as it appeared. This uncertainty becomes more troubling when considered against the backdrop of the approaching observational gap, the most critical period for understanding 3I Atlas's true nature. The weeks surrounding perihelion, when solar heating reaches maximum intensity, will occur largely hidden from Earth-based telescopes. If the comet undergoes its most dramatic transformations during this period, researchers may never understand what they witnessed in September. Dr. Carrie Leese, who studies interstellar objects at the European Southern Observatory, expressed the frustration felt by many researchers. The exact moment when 3I Atlas might reveal its most significant secrets coincides with the period when Earth-based astronomy becomes least capable of observing it. The timing represents what she termed a cosmic conspiracy against scientific understanding. The debates extend beyond simple brightness measurements to fundamental questions about what 3I Atlas represents. As a physical object, its chemical composition, revealed through spectroscopic analysis, shows ratios of carbon dioxide to water vapor unlike those typical of solar system comets. This difference could indicate formation conditions radically different from our local environment. Or it might reflect chemical processing that occurred during millions of years of interstellar travel. Amateur astronomy communities have become crucial contributors to the 3I Atlas monitoring effort, providing continuous observations that professional observatories cannot always maintain. However, the scattered nature of amateur measurements introduces its own complications. Different observers, using different equipment and processing techniques, sometimes report brightness values that disagree by significant amounts, making it challenging to determine whether observed variations represent real changes in the comet or measurement artifacts. The European Space Agency's tracking efforts, coordinated through their Space Situational Awareness Program, attempt to reconcile these measurement discrepancies while maintaining continuous monitoring of 3I Atlas's trajectory and brightness evolution. Their analysis confirms the general trend toward enhanced brightness, but acknowledges the difficulties in quantifying exactly how much. The comet exceeds theoretical predictions. Social media within the astronomical community reflects a mixture of scientific excitement and professional caution that characterizes response to 3I Atlas. Researchers share preliminary images and brightness measurements while carefully noting the uncertainties and limitations in their data. The tone suggests scientists are aware they're observing something potentially significant while remaining professionally skeptical about drawing premature conclusions. The green color change documented in mid-September adds another layer to the scientific intrigue. While diatomic carbon emission can explain the observed coloration, the timing and intensity of the green glow don't perfectly match the chemical composition indicated by earlier spectroscopic observations. This apparent discrepancy between what researchers measure chemically and what they observe visually suggests either measurement limitations or chemical processes more complex than standard models. Predict. Conference presentations scheduled for the American Astronomical Society's Division for Planetary Sciences meeting include multiple talks focused on 3I Atlas, observations and theoretical modeling efforts. The abstracts reveal research groups worldwide attempting to understand not just what 3I Atlas is doing, but why existing models fail to predict its behavior accurately. Sense of urgency among researchers reflects more than scientific curiosity. It represents the recognition that opportunities to study interstellar objects remain extraordinarily rare, with only 3 confirmed interstellar visitors in human history. Each object provides irreplaceable data about conditions in other star systems and the processes that govern small body formation throughout the galaxy. International collaboration has intensified as the observational window narrows. Telescopes in Chile, Hawaii, the Canary Islands, and Australia coordinate observations to maximize coverage as 3I Atlas approaches the solar conjunction period that will end routine Earth-based monitoring. Each facility contributes unique capabilities, from high-resolution imaging to specialized spectroscopic instruments, in an effort to extract maximum scientific value from the remaining observation opportunities. The professional astronomical community also grapples with public communication Challenges surrounding 3I Atlas. Media. Reports sometimes overstate the certainty of scientific conclusions or sensationalize aspects of the comet's behavior that researchers themselves acknowledge as uncertain. Balancing public interest in this rare interstellar visitor with the complexities and uncertainties inherent in ongoing research demand meticulous consideration of how scientific findings are communicated and understood. Risk assessment frameworks designed for potentially threatening asteroids gain renewed significance in relation to 3I Atlas, not due to any terrestrial threat posed by the comet, but because its erratic characteristics expose gaps in our current comprehension of how minor celestial bodies respond to solar radiation. When scientists struggle to accurately forecast the conduct of 3I Atlas, legitimate concerns emerge regarding this dependability of predictive models employed to evaluate hazards from other cosmic objects. The growing enthusiasm surrounding 3I Atlas embodies a core principle of scientific exploration: the acknowledgement that natural phenomena consistently exhibit greater complexity and generate more unexpected outcomes than human theoretical frameworks anticipate. With October's arrival and the increasing difficulty of Earth-based observation, astronomers find themselves wishing that spacecraft distributed across the solar system might witness the phenomena that ground-based telescopes will be compelled to overlook. As Earth prepares to lose visual contact with 3I Atlas amid solar brightness, another celestial body positions itself to witness one of the most remarkable astronomical occurrences in contemporary history. On October 3, 2025, Mars will facilitate humanity's nearest encounter with an interstellar traveler, providing spacecraft in Martian orbit exceptional chances to study 3I Atlas from a perspective that Earth-based instruments can only imagine achieving. The celestial geometry proves remarkably favorable. When 3I Atlas passes Mars at approximately 30 million kilometers, roughly 0.2 astronomical units, several spacecraft currently functioning in Martian orbit will possess the capability to redirect their instruments toward this cosmic wanderer. The chronology positions these observations mere days before superior conjunction renders Earth-based monitoring impossible, establishing a vital transition from terrestrial to space-based surveillance. The European Space Agency's Mars Express Orbiter, deployed in 2003 and still operating well beyond its intended mission duration, carries the high-resolution stereo camera that has charted Martian topography in extraordinary detail for over 20 years. Though engineered for planetary geology investigations, HRSC possesses the sensitivity and clarity potentially necessary to obtain detailed imagery of 3I Atlas's nucleus and inner coma architecture. Dr. Colin Wilson, project scientist for the ExoMars Trace Gas Orbiter, verified that mission coordinators are assessing possibilities for both the color and stereo surface imaging system known as CASIS, and the nadir and occultation for Mars discovery spectrometer Nomad to examine the interstellar traveler. These instruments, crafted to investigate Martian atmospheric characteristics and terrain features, might possess the capability to identify chemical indicators within 3I Atlas's expanding coma. Mars Reconnaissance Orbiter offers perhaps the most fascinating prospects for comprehensive observations. The High-Resolution Imaging Science Experiment. HIRISE consistently captures surface characteristics smaller than 1 meter across from its orbital elevation of approximately 300 kilometers above Mars, although 3I Atlas will traverse at a considerably greater distance. HIRISE's remarkable resolution might discern structural features of the comet's nucleus that remain undetectable to Earth-based telescopes. The MAVEN spacecraft, NASA's Mars Atmosphere and Volatile Evolution mission, carries spectrographic equipment specifically engineered to examine atmospheric composition and behavior. These technical capabilities could demonstrate considerable value for investigating the chemical makeup of 3I Atlas's coma, especially the carbon dioxide-dominant gases that characterize its spectroscopic profile. Nevertheless, the observational possibilities arrive with substantial technical obstacles. All Mars orbiters were conceived and calibrated for examining the red planet itself, not for monitoring rapidly moving objects against the stellar backdrop. The spacecraft's directional systems, developed for observing a substantial nearby planet, must be recalibrated to track a diminutive distant target traveling at interstellar speeds. Signal intensity constitutes the most elemental constraint. Even at its nearest approach to Mars, 3I Atlas will manifest as extraordinarily dim to spacecraft instruments designed for planetary rather than deep space examinations. The comet's magnitude, approximated around 12 to 14, even during its luminosity enhancement phase, challenges the detection capabilities of most Mars orbiter cameras and SPECTROMETERS. Dr. Wilson recognized these constraints in recent correspondence with the International Astronomical Collective, observing that while Mars-based examinations of 3I Atlas remain theoretically feasible, the genuine scientific yield depends on variables including the comet's luminosity at closest approach, atmospheric circumstances on Mars, and the particular geometric configurations required for successful targeting. The benefit of Mars-based observations transcends simple proximity. The viewing geometry from Mars during the October 3rd flyby furnishes a perspective on 3I Atlas unavailable from Earth. Solar phase angles, the angle formed between the Sun, comet, and observer will differ substantially between Mars and Earth viewpoints, potentially disclosing details of coma architecture and tail geometry, concealed from terrestrial telescopes. Solar-wind interactions constitute another domain where Mars orbiters might contribute distinctive observations. 3I Atlas's encounter with the solar wind, the stream of electrically charged particles flowing outward from the Sun could generate phenomena detectable by the plasma and magnetic field instruments transported by several Mars missions. These interactions might unveil information about the comet's internal architecture and composition through alterations in its magnetic and electrical characteristics. The European Space Agency's coordination initiatives for the Mars flyby observations necessitate unprecedented collaboration between missions conceived for entirely different scientific purposes. Mars Express, initially planned for surface geology and atmospheric investigations, finds itself repurposed as an interstellar object observatory. The Trace Gas Orbiter, concentrated on methane identification and atmospheric chemistry, must modify its instruments for cometary spectroscopy. Temporal restrictions add intricacy to observation preparation. Mars orbiters adhere to predetermined schedules for routine planetary observations, communication intervals with Earth, and spacecraft maintenance operations. Incorporating 3I Atlas observations into these timetables requires meticulous coordination to prevent interference with primary mission goals while optimizing scientific possibilities. The data relay obstacles are considerable. Mars orbiters typically establish communication with Earth during designated intervals when both planets' orbits create advantageous geometry for radio transmission. Imagery and spectra of 3I Atlas must vie with routine planetary science data for restricted communication bandwidth, potentially postponing the dissemination of observations by weeks or months. Ground-based assistance for Mars orbiter observations necessitates coordination among multiple space agencies and research facilities worldwide. The European Space Operations Center in Germany, NASA's Jet Propulsion Laboratory in California, and other establishments must collaborate to devise observation sequences analyze incoming data, and circulate results to the International Scientific Collective. The scientific merit of successful Mars-based observations could prove revolutionary for comprehending 3I Atlas. High-resolution imaging might resolve the nucleus, dimensions, and configuration with unprecedented exactness, resolving controversies about the comet's physical parameters and structure. Spectroscopic examinations could detect molecular varieties invisible from Earth-based telescopes, exposing chemical compositions that retain information about the comet's formation, surroundings, structural particulars of the coma and tail, especially the peculiar sunward-directed plume that has mystified researchers, might become more comprehensible when observed from Mars's distinctive perspective. The divergent solar phase angle could clarify whether the anti-tail architecture results from authentic sunward material ejection or represents a projection phenomenon that appears different from various observation angles. Pragmatism requires tempering expectations about what Mars orbiters can accomplish. Even under ideal circumstances, the scientific harvest from these observations will likely comprise a handful of images and spectra rather than exhaustive monitoring endeavors. The instruments were never engineered for this category of observation, and their capabilities may demonstrate inadequate to resolve the fundamental inquiries about 3I Atlas's character and conduct. Achievement depends on factors beyond human authority. If 3I Atlas experiences another brightening occurrence before October 3rd, it might become perceptible to Mars orbiter instruments that would otherwise find it too faint to detect. Alternatively, if the comet diminishes from its current enhanced luminosity levels, even the most optimistic observation scenarios might produce no valuable data. The Mars flyby constitutes humanity's optimal opportunity to sustain surveillance of 3I Atlas during the crucial weeks when Earth-based telescopes forfeit sight of this interstellar visitor. As terrestrial astronomy prepares for an enforced silence extending through early November, the mechanical sensors orbiting Mars offer the sole prospect of witnessing what may prove to be the most theatrical phase of all 3I Atlas's encounter with our solar system. Whether these observations succeed or fail, they signify a new epoch in how humanity examines visitors from other stellar systems, exemplifying our expanding capacity to coordinate observations across multiple worlds, even as the subjects of our scrutiny race passed at interstellar velocities. The calculations of celestial mechanics remain utterly indifferent to human inquisitiveness. As October advances and 3I Atlas perpetuates its inexorable approach toward the Sun, the geometric actualities of orbital motion conspire to withdraw our interstellar visitor, precisely when it might disclose its most profound mysteries. Superior conjunction that interval when 3I Atlas appears too proximate to the Sun's position in our sky for practical observation transforms one of the most consequential astronomical events in recent memory into a cosmic vanishing performance. The chronology unfolds with pitiless exactitude. In early October, 3I Atlas descends below 30 degrees of solar elongation, the boundary where severe observational complications commence for ground-based telescopes. Atmospheric dispersion of sunlight generates a brightening sky background that overwhelms the feeble signal from our interstellar visitor. Professional observatories, with their advanced adaptive optics and light collecting capacity, can prolong observations marginally longer than amateur telescopes. But even they confront increasingly futile conditions. By mid-October, elongation diminishes to less than 20 degrees, effectively terminating routine observations from Earth's surface. The comet doesn't vanish abruptly. It fades progressively into the solar brilliance like a star at dawn, becoming increasingly arduous to detect until observation becomes unattainable rather than merely demanding. This gradual transformation makes it challenging to identify precisely when Earth loses visual contact with 3I Atlas. But the practical outcome remains identical. Our primary window into the comet's behavior closes just as solar heating approaches its maximum intensity. The conjunction interval extends through early November, encompassing approximately 4 to 5 weeks when 3I Atlas remains effectively invisible from Earth. This isn't merely an inconvenient interruption in observations. It represents the complete forfeiture of our ability to monitor the comet during what theoretical models forecast should be its most vigorous period. Peak outgassing, maximum tail development, possible fragmentation occurrences, and other spectacular phenomena could all transpire hidden from human view. The harsh irony becomes more evident when considered against the context of 3I Atlas's recent conduct. The rapid luminosity increase observed in September, the unusual anti-tail architecture, and the distinctive green pigmentation all indicate an object experiencing fundamental transformations as it encounters our sun's radiation. Logic suggests that these metamorphoses should intensify as solar heating escalates, potentially reaching spectacular magnitudes near perihelion in late October. Yet perihelion occurs almost precisely at the midpoint of the conjunction interval when 3I Atlas appears. Nearest to the Sun in Earth's sky, an observation becomes most impossible. The chronology couldn't be more unfortunate for comprehending what this interstellar visitor truly becomes when subjected to maximum solar influence. It's as though the universe deliberately orchestrated for the most captivating portion of the spectacle to occur behind a drawn curtain. The physics underlying superior conjunction involve no conspiracy against scientific discovery merely the geometric ramifications of observing from a planet orbiting the identical star as our target. As 3I Atlas approaches perihelion, its apparent location in the sky necessarily approaches the Sun's position. The angular separation decreases steadily until the comet appears to transit behind our star, creating observational circumstances that no magnitude of technological sophistication can surmount. Professional astronomers encounter this limitation with exasperating regularity when studying objects that approach near to the Sun's location. Solar observing satellites, like the Solar and Heliospheric Observatory, SOHO, can occasionally track comets during conjunction intervals using coronagraphs that obstruct the Sun's direct illumination. However, 3I Atlas's trajectory doesn't pass sufficiently near to the Sun for detection by these specialized instruments, which typically observe objects within a few solar radii of our star dot. The conjunction gap establishes unprecedented obstacles for a scientific community habituated to continuous monitoring capabilities. Contemporary astronomy relies substantially on long-term observation, campaigns that track objects through complete cycles of activity. Comets, specifically, require extended monitoring to differentiate between temporary outburst events and sustained behavioral changes. The enforced observational interruption during 3I Atlas's most critical period eliminates the possibility of this type of comprehensive analysis. Spacecraft positioned throughout the solar system offer restricted alternatives to ground-based observations, but their capabilities remain constrained by original mission architectures focused on planetary rather than cometary investigations. The Mars orbiters discussed previously provide the most encouraging near-term possibilities, but their observations will be transient snapshots rather than the continuous monitoring necessary to fully comprehend 3I Atlas's evolution. The European Space Agency's Bepi-Colombo mission, presently en route to Mercury, follows a trajectory that might furnish occasional opportunities to observe 3I Atlas from a different vantage point than Earth. However, the spacecraft's instruments are calibrated for Mercury investigations, and the geometric prerequisites for comet observations may not align. favorably with mission operational limitations. NASA's Parker Solar Probe, engineered to investigate the Sun's corona and solar wind, operates in the inner solar system, where it might theoretically encounter 3I Atlas's tail or coma material. However, the probe's highly elliptical orbit and emphasis on solar, rather than cometary phenomena, restrict its utility for systematic comet observations. The conjunction period also establishes challenges for theoretical modeling initiatives, attempting to forecast 3I Atlas's behavior. Computer simulations of comet activity depend on observational data to calibrate their predictions and authenticate their accuracy. The 4 to 5 week gap in observations eliminates crucial data points that modelers require to refine their comprehension of how this interstellar object responds to solar heating. When Earth-based observations recommence in November or early December, 3I Atlas will likely have transformed dramatically from the object astronomers examined in September. The comet may have brightened further, possibly developing spectacular tail structures visible through amateur telescopes. Alternatively, it might have faded considerably if volatile materials became exhausted during the unobserved perihelion passage. More dramatically, 3I Atlas might have fragmented into multiple components during its closest approach to the Sun's position. Comet fragmentation isn't unusual near perihelion, where tidal forces and thermal stresses can overcome the weak gravitational binding holding nucleus materials together. If fragmentation occurs during conjunction, Earth-based observers will face the challenging assignment of identifying and tracking multiple objects when observations become feasible again. The resumption of observations in late November or December will necessitate careful preparation and coordination among observatories worldwide. 3I Atlas will emerge from conjunction in a different sector of the sky, requiring telescopes to locate and reacquire the comet after weeks of invisibility. The object's brightness, position, and appearance may have changed sufficiently to complicate identification and tracking endeavors. Public interest in 3I Atlas faces its own conjunction-related challenges. Media coverage of astronomical events typically relies on dramatic imagery and continuous updates to sustain audience engagement. The enforced silence during the conjunction period eliminates the steady stream of new observations that maintain public attention, potentially diminishing interest. Just as the comet experiences its most significant transformations, educational opportunities also suffer during the conjunction gap. Schools and amateur astronomy groups frequently utilize bright comets as instruments for teaching about solar system dynamics and observational techniques. 3I Atlas's disappearance into solar glare eliminates these opportunities during what might be the comet's most photogenic period, when tail development and nuclear activity could provide the most visually spectacular educational content. Conjunction period functions as a reminder of awe. Astronomy's fundamental limitations despite centuries of technological advancement. Humans remain tethered to their home planet for most astronomical observations, subject to the geometric constraints imposed by Earth's position relative to observed objects and the Sun. Even our most sophisticated space-based telescopes cannot completely transcend these limitations when objects approach too close to our star's position. As the first Atlas vanishes into solar glare, the astronomical community prepares for a period of conjecture and theoretical modeling based on incomplete data. The question isn't whether the comet will change during its hidden passage. It's whether those changes will be comprehensible when observations resume, or whether the conjunction gap will leave permanent mysteries about what transpired during the most critical phase of this interstellar visitors' encounter with our Sun's orbit, deep within the solar glare that blinds Earth's telescopes. 3I Atlas prepares for its rendezvous with destiny. On October 29th to 30th, 2025, This interstellar wanderer will achieve perihelion, its closest approach to the Sun, at approximately 1.36 to 1.4 astronomical units. Concealed from human observation, a comet will experience solar radiation intensities unlike anything encountered in its multi-million-year journey between stellar systems, potentially experiencing transformations that could redefine our understanding of interstellar objects. The velocity evolution alone narrates a tale of cosmic violence, currently racing through space at tens of kilometers per second. The first Atlas will attain its maximum velocity near perihelion, potentially reaching 68 kilometers per second, or approximately 152,000 miles per hour. To appreciate this extraordinary speed, consider that Earth maintains its stable orbit around the Sun at roughly 30 kilometers per second. 3I Atlas will be traveling more than twice as rapidly as our entire planet, carrying kinetic energy accumulated during its epic voyage across the galaxy. Physics forecasts that perihelion will initiate the most traumatic phase of 3I Atlas's solar system encounter. As solar heating reaches maximum intensity, the temperature of the comet's nucleus will soar, potentially activating volatile compounds that have remained stable throughout its interstellar voyage. Water ice, carbon dioxide, carbon monoxide, and more exotic frozen gases could all begin sublimating simultaneously, generating an explosive expansion of the coma that might dwarf the already unprecedented dimensions observed in September. Increased outgassing could produce spectacular dust jets erupting from discrete locations on the nuclear surface. These jets, formed when subsurface volatile deposits find pathways to escape, can create fountain-like structures, extending thousands of kilometers into space. The sunward-pointing anti-tail that has perplexed observers might intensify dramatically, or entirely new tail structures could emerge as different volatile compounds begin contributing to the coma for the first time. Theoretical models suggest that 3I Atlas's carbon dioxide-rich composition might produce perihelion behavior, unlike that of typical solar system comets. Carbon dioxide sublimes more readily than water ice at the temperatures expected near perihelion, potentially creating gas production rates that exceed those of water-dominated comets by significant factors. This enhanced activity could manifest as rapid changes in brightness, coma size, and tail structure occurring over periods of hours rather than the days or weeks typically associated with comet evolution. The possibility of fragmentation looms over perihelion, predictions like a shadow of uncertainty. Comets represent some of the most fragile objects in the solar system, held together by weak gravitational forces and the structural integrity of their icy matrices. The thermal stresses induced by intense solar heating, combined with the mechanical forces generated by explosive outgassing, can overcome these binding forces and tear nuclei apart. Fragmentation events can unfold with dramatic suddenness. A comet that appears stable during its approach to perihelion can split into multiple pieces within hours as thermal gradients create structural weaknesses, or gas pressure eruptions excavate material from the nucleus interior. If 3I Atlas undergoes fragmentation, Earth-based observers will face the complex task of identifying and tracking multiple objects when observations resume in November. The historical precedent for comet fragmentation near perihelion includes spectacular examples like Comet Shoemaker-Levy 9, which broke apart under Jupiter's tidal forces before impacting the planet in 1994. More recently, Comet Ice Owen disintegrated during its extremely close approach to the Sun in 2013, creating a debris cloud that dispersed rapidly as it moved away from perihelion. However, fragmentation isn't inevitable. The structural integrity of 3I Atlas depends on factors including nucleus composition, internal porosity, rotation rate, and the specific thermal stresses generated by its unique volatile mixture. Interstellar objects might possess structural characteristics that differ significantly from solar system comets, potentially making them more or less susceptible to thermal disruption. The speed at which 3I Atlas passes through perihelion also influences fragmentation risk. Unlike some comets that linger near their closest solar approach, 3I Atlas will sweep past perihelion relatively quickly due to its hyperbolic trajectory. This rapid passage limits the duration of peak heating, potentially reducing the cumulative thermal stress experienced by the nucleus. If 3I Atlas survives perihelion intact, the post-perihelion period should reveal an object transformed by its encounter with intense solar radiation. The coma might expand to even larger dimensions as peak gas production rates distribute material across unprecedented volumes of space. New chemical species liberated from subsurface deposits by deep heating could appear in spectroscopic observations for the first time. Color changes beyond the green emission already observed might develop as different molecular species begin fluorescing under solar ultraviolet radiation. Complex organic compounds, if present in the nucleus, could break down into simpler fragments that emit light at characteristic wavelengths, potentially creating a rainbow of emissions across the visible spectrum. The anti-tail phenomenon that has characterized the first Atlas observations might evolve dramatically near perihelion. Enhanced dust production could create multiple tail structures pointing in different directions as particles of various sizes respond differently to solar radiation pressure. The resulting geometry could provide crucial information about the nucleus rotation rate, surface composition, and internal structure. Dust grain analysis becomes particularly important during the perihelion period. The size, distribution, and composition of particles ejected from the nucleus reflect the internal structure and formation conditions of the original object. Large grains might indicate a loosely consolidated nucleus with significant void spaces, while fine dust could suggest a more compact structure or specific chemical compositions that favor the production of small particles. Magnetic and plasma environment near perihelion adds another layer of complexity to 3I Atlas's behavior. The solar wind-charged particles streaming outward from the sun interacts with the ionized gases in the comet's coma to create complex electromagnetic phenomena. These interactions can accelerate particles to high velocities, create visible glows in the coma, and influence the development of plasma tails that extend millions of kilometers behind the nucleus. Temperature measurements during perihelion, if obtainable through spacecraft observations, could provide fundamental insights into 3I Atlas's thermal properties and internal structure. Different volatile compounds sublimate at specific temperatures, creating a chemical thermometer that reveals the heating progression within the nucleus as solar radiation penetrates its surface layers. The aftermath of perihelion will depend critically on how much volatile material 3I Atlas contains and how efficiently that material can escape through the nuclear surface. Objects with large volatile reserves might continue showing enhanced activity for weeks or months after perihelion, while those with limited volatile content could fade rapidly as their surface layers become depleted. Gravitational perturbations from the Sun's intense gravitational field near perihelion could also affect 3I Atlas's future trajectory. While the comet will definitely continue outward on its hyperbolic path, small changes in velocity could alter the timing and geometry of future encounters with outer solar system planets, particularly Jupiter in 2026. The perihelion passage represents the climax of 3I Atlas's solar system encounter, the moment when billions of years of interstellar evolution meet the intense radiation environments surrounding our star. Whether this meeting produces spectacular displays of cosmic pyrotechnics or quiet, structural transformations hidden within an expanding coma, the perihelion will fundamentally alter 3I Atlas from the object that entered our solar system into something new and unprecedented. The question that will haunt astronomers through the conjunction period is whether 3I Atlas will emerge from its hidden perihelion passage recognizable as the same object that captivated observers in September, or as something entirely transformed by its encounter with our sun's most intense radiation. The answer lies hidden in solar glare, awaiting the patient geometry of orbital mechanics to reveal what perihelion has wrought. To understand the significance of 3I Atlas in its bizarre behavior, we must look backward through the brief but revolutionary history of confirmed interstellar visitors. Only 2 objects before our current visitor have been definitively identified as originating beyond our solar system, and each has rewritten astronomical textbooks in its own unique way. The story they tell together is one of cosmic diversity that challenges every assumption about how these wandering messengers from other star systems should behave. 1I Oumuamua arrived first. Discovered on October 19, 2017, by the Panoramic Survey Telescope and Rapid Response System PAN-STARRS in Hawaii. Initially classified as an asteroid due to its lack of visible coma, Oumuamua quickly proved that interstellar objects would not conform to Earth-based expectations. Its highly elongated shape, roughly 400 meters long and 40 meters wide, resembled no asteroid or comet previously observed in our solar system. More puzzling still, Oumuamua exhibited non-gravitational acceleration as it moved away from the sun, speeding up in ways that couldn't be explained by gravitational forces alone. This mysterious acceleration sparked debates that continue today. Was it outgassing from hidden volatile deposits, solar radiation pressure acting on an unusually shaped object, or something more exotic that pushed the boundaries of conventional physics? The absence of a detectable coma around Oumuamua contradicted expectations for objects containing the volatile ices typical of comets. Yet something was clearly acting on the object to produce the observed acceleration. The resolution, if it can be called that, involved invoking outgassing so minimal that it remained below detection thresholds, while still generating enough force to alter Oumuamua's trajectory. 2I Borisov, discovered on August 30, 2019, by amateur astronomer Gennady Borisov in Crimea, presented a completely different personality. Unlike its predecessor's enigmatic behavior, Borisov appeared refreshingly normal at first glance, a classic comet complete with fuzzy coma and developing tail structures that matched theoretical expectations for objects heated by solar radiation. However, detailed analysis revealed that Borisov's apparent normality masked chemical compositions, unlike anything found in native solar system comets. Spectroscopic observations showed carbon monoxide concentrations significantly higher than those typical of local comets, suggesting formation conditions in a protoplanetary disk with different temperature and chemical gradients than our own solar nebula. The dust-to-gas ratio in Borisov's coma also differed from solar system norms, indicating either different formation processes or evolutionary changes that occurred during its interstellar journey. These subtle but significant chemical differences provided the first direct evidence that other star systems produce comets with compositions reflecting their unique formation environments. Now 3I Atlas enters this exclusive club with characteristics that make both of its predecessors seem mundane by comparison. The carbon dioxide-rich coma detected by SPHERX and confirmed through follow-up observations represents the most extreme compositional departure from solar system norms yet observed in an interstellar visitor. The CO2 to water vapor ratio suggested by James Webb Space Telescope analysis indicates formation conditions even more exotic than those that produced Borisov. The sunward-pointing anti-tail structure of 3I Atlas has no parallel in previous interstellar object observations. While Oumuamua showed no tail structures due to its apparent lack of significant outgassing, and Borisov displayed conventional comet tails streaming away from the sun. 3I Atlas creates geometry that defies basic principles of comet physics as understood through centuries of observation. The rapid brightening trend documented in September 2025 adds another unique characteristic to 3I Atlas's growing list of anomalies. Neither Oumuamua nor Borisov exhibited such dramatic short-term brightness variations, suggesting that 3I Atlas undergoes processes, whether outgassing events, structural changes, or surface evolution operating on timescales faster than those typical of previously studied interstellar objects. Size comparisons reveal interesting patterns in the interstellar visitor population. Oumuamua's dimensions, estimated at roughly 440 meters, made it significantly larger than typical small asteroids, but smaller than most active comet nuclei. Borisov's nucleus diameter, estimated at approximately 1 kilometer, fell within the normal range for solar system comets. 3I Atlas presents size estimation challenges that reflect the uncertainty surrounding its fundamental nature. Hubble Space Telescope observations suggest a nucleus diameter somewhere between 0.32 and 5.6 kilometers, a range that encompasses both small and moderately large comet nuclei. The uncertainty arises from difficulties in separating the nucleus from its extensive coma, itself a unique characteristic that distinguishes 3I Atlas from its interstellar predecessors. Chemical analysis capabilities have evolved significantly between the discovery of each interstellar visitor, allowing progressively more detailed composition studies. Oumuamua's brief visibility period and lack of significant outgassing limited chemical analysis to surface reflection properties and rough density estimates. Borisov's more conventional comet behavior enabled spectroscopic detection of water vapor, carbon monoxide, and various other molecular species typical of comet comas. 3I Atlas benefits from the most advanced observational capabilities yet applied to an interstellar object. James Webb Space Telescope's infrared spectroscopy, Hubble's high-resolution imaging, and ground-based observatories equipped with next-generation spectrographs provide unprecedented detail about chemical composition, physical structure, and temporal evolution. The orbital characteristics of each interstellar visitor also tell their own stories about galactic dynamics and the processes that eject objects from their birth star systems. Oumuamua approached the solar system from the direction of the star Vega, though its journey time exceeded Vega's age, indicating a more complex galactic trajectory. Its hyperbolic excess velocity, the speed it would retain after escaping solar gravitational influence, measured approximately 26 kilometers per second. Borisov's trajectory suggested origin from a region of space containing young, hot stars in the constellation Cassiopeia, with a hyperbolic excess velocity of approximately 32 kilometers per second. The higher velocity indicated either ejection from a more massive star system or acceleration through gravitational interactions. During its interstellar journey, 3I Atlas carries the highest hyperbolic excess velocity yet measured for an interstellar object, estimated at approximately 39 kilometers per second. This extreme velocity suggests either formation around a particularly massive star or acceleration through multiple gravitational encounters during its journey through the galaxy. The velocity also influences the object's behavior near perihelion, as higher speeds reduce the time available for solar heating to penetrate deep into the nucleus interior. The discovery intervals between interstellar visitors provide insights into their population in the galaxy. The 2-year gap between Oumuamua and Borisov followed by the 6-year interval before 3I Atlas, suggests that such objects pass through the inner solar system regularly but remain difficult to detect due to their small sizes and brief visibility periods. Statistical analysis of the 3 confirmed interstellar objects indicates that each represents a different type of small body formation process, suggesting enormous diversity in how other star systems produce and eject comets and asteroids, rather than converging toward typical characteristics. Each new interstellar visitor has expanded the range of possible behaviors and compositions. The unique characteristics of 3I Atlas, the unprecedented coma size, anti-tail structure, chemical composition, and brightness evolution suggest that interstellar object diversity encompasses phenomena not yet imagined by theoretical models based on solar system experience. Each visitor teaches new lessons about planetary formation, processes throughout the galaxy, while simultaneously raising new questions about what other types of interstellar objects await discovery. As 3I Atlas continues its hidden passage through perihelion, astronomers can only speculate about whether its post-conjunction appearance will add new entries to the growing catalog of interstellar object peculiarities. The pattern established by Oumuamua and Borisov suggests that 3I Atlas will continue surprising researchers with behaviors that challenge fundamental assumptions about small body physics. The lesson emerging from all 3 interstellar visitors is that the galaxy produces small bodies through processes far more diverse and complex than those operating in our local solar system. Each object carries chemical and physical signatures of formation, environments that differ dramatically from our own cosmic neighborhood, providing direct samples of planetary system evolution occurring throughout the Milky Way. The scientific community's response to 3I Atlas resembles a detective story where crucial evidence remains locked away, forcing researchers to construct theories from incomplete clues, while the most important information lies hidden behind solar glare. Multiple competing hypotheses. Researchers continue their efforts to understand the comet's peculiar characteristics, though every explanation they develop introduces fresh uncertainties that might persist without resolution until post-conjunction observations supply the absent components of this interstellar enigma. The debate over the nucleus's dimensions and configuration demonstrates the fundamental obstacles confronting 3I Atlas investigators. Hubble Space Telescope measurements have constrained the size projection to a range spanning 0.32 to 5.6 kilometers in diameter. Yet this extensive range demonstrates the complexity of distinguishing the solid core from its vast surrounding coma. This uncertainty carries significance because dimensional measurements directly influence computations of mass, density, surface territory available for gas release, and structural integrity during perihelion severe heating. Various measurement approaches yield contradictory outcomes. Thermal analysis derived from infrared measurements points toward a more compact nucleus featuring high albedo, a reflective exterior that efficiently disperses sunlight. Visual spectrum examination suggests a more substantial, darker core that captures greater solar energy. This conflict might stem from variations in surface makeup, measurement imprecision, or basic misunderstandings regarding 3I Atlas's response to solar thermal input. Compositional examination confronts its own collection of paradoxes. James Webb Space Telescope spectroscopic data unambiguously identifies carbon dioxide as the prevailing volatile component in 3I Atlas's coma, with CO levels surpassing water vapor concentrations by considerable margins. This chemical profile contrasts sharply with solar system comets, where water ordinarily dominates volatile reserves. Nevertheless, the carbon dioxide prevalence generates theoretical difficulties in accounting for other witnessed features. The emerald coloration that emerged in September conventionally signals diatomic carbon discharge. Yet CO-rich, outgassing doesn't spontaneously generate the carbon-containing molecules responsible for green luminescence either. The spectroscopic examination overlooked significant chemical components, or the green hue results from mechanisms more intricate than straightforward molecular fluorescence, ground-based, spectroscopic measurements from the Very Large Telescope and other premier observatories have identified supplementary molecular varieties, including cyanide derivatives and assorted organic compounds. These identifications suggest chemical intricacy beyond the straightforward CO dominance revealed by space-based measurements, implying that 3I Atlas harbors a varied collection of both elementary and sophisticated carbon-containing substances. The anti-tail formation presents arguably the most bewildering observational conundrum. Traditional comet mechanics dictate that solar radiation force should propel gas and dust away from the sun, generating tails that extend radially outward from the solar axis. 3.1 Atlas appears to defy this foundational principle by expelling matter that creates formations, pointing toward the sun instead of away from it. Dr. Keating and Dr. Lee's recent theoretical examination, presently undergoing peer assessment, proposes that the anti-tail originates from atypical dust grain dimension distributions, combined with particular ejection geometries from the nuclear exterior. Their framework suggests that substantial dust fragments ejected sunward with adequate initial momentum can counteract solar radiation force to produce the witnessed forward-extending formations. However, alternative frameworks invoke distinct physical processes. Some investigators propose that electromagnetic phenomena interactions between electrically charged dust fragments and solar magnetic fields could redirect matter in unexpected trajectories. Others maintain that 3I Atlas's rotational condition generates temperature imbalances that focus outgassing in particular directions independent of solar radiation force. The rotation cycle of 3I Atlas remains undetermined, despite months of observational efforts. Light curve examination, which measures luminosity fluctuations caused by an asymmetrically shaped nucleus rotating in sunlight, has failed to disclose distinct periodic patterns. This lack of detectable rotational indicators could suggest either exceptionally slow rotation, an almost spherical configuration, or rotational intricacy that masks straightforward periodic variations. Rotational condition influences numerous aspects of comet characteristics. Swiftly spinning bodies experience centrifugal pressures that can affect outgassing distributions and structural steadiness. Gradually rotating comets develop temperature disparities between illuminated and shadowed hemispheres that concentrate volatile discharge in heated zones. The undetermined rotational properties of 3I Atlas complicate attempts to simulate its thermal progression and forecast future characteristics. The brightness progression, documented in September, presents its own analytical obstacles. Multiple observation systems confirmed that 3I Atlas grew substantially more luminous than theoretical forecasts, though the scale of this deviation remains disputed. Some watchers report luminosity increases equivalent to several magnitude increments, while others suggest more moderate enhancements that remain within the typical spectrum of comet fluctuation. The inconsistencies emerge partially from measurement complications. 3.1 Atlas persists near the detection thresholds of most telescopes, rendering precise photometry demanding even under optimal circumstances. Different watchers employ different reference stars, filter arrangements, and reduction methodologies that can introduce systematic biases into brightness calculations. More fundamentally, the absence of baseline measurements complicates brightness pattern examination. Unlike periodic comets that have been monitored through multiple returns, 3I Atlas represents a singular opportunity subject with no historical records for reference. Investigators must depend on theoretical frameworks based on solar system comets to determine anticipated characteristics. But these frameworks may not extend to bodies formed in alternative star systems. Origin investigations attempt to trace 3I Atlas's path backward through the galaxy to pinpoint its probable formation site. Present kinematic evaluation suggests the comet originated somewhere within the Milky Way's thin disk, the flat star-dense zone where most contemporary star formation transpires. However, the imprecision in measured location and velocity propagate backward through time, generating progressively larger error regions that encompass multiple potential source territories. The galactic origin inquiry holds ramifications for comprehending 3I atlases, composition and duration of existence. Bodies expelled from young star systems might preserve distinct chemical markers than those originating from older, more developed stellar contexts. The carbon dioxide prevalence could represent formation in a moon, protoplanetary disk with temperature and chemical gradients unlike those that generate solar system bodies. Structural steadiness represents another domain of vigorous discussion. The substantial coma and anti-tail formation indicate robust outgassing that could suggest either a volatile abundant nucleus or one experiencing structural breakdown. Some investigators propose that 3I Atlas represents a loosely connected assembly of smaller bodies, a rubble aggregate, held together by feeble gravitational attractions that could disintegrate under thermal or tidal pressures. Alternative frameworks treat 3I Atlas as a monolithic body with atypical surface characteristics or internal architecture that generates the witnessed outgassing. Distributions. The differentiation matters for forecasting characteristics. Near perihelion, where thermal pressures and tidal forces achieve maximum strength, the 2 astronomical unit activation moment witnessed in early September remains inadequately comprehended. The abrupt escalation in activity as 3I Atlas crossed this solar distance could signify the triggering of particular volatile substances that sublimate at specific temperatures. Alternatively, it might represent structural modifications in the nucleus that revealed previously concealed volatile reserves to solar heating. Distinct volatile varieties sublimate at distinct solar distances, establishing a natural progression of activation as comets advance toward perihelion. Water ice commences substantial outgassing around 3 astronomical units, while carbon dioxide can sustain activity at considerably greater separations. The particular characteristics of 3I Atlas suggest a sophisticated blend of volatile substances with activation temperatures that don't correspond to solar system comet. Observations. The observational interruption during conjunction generates additional ambiguity about which theoretical frameworks best account for 3I Atlas's characteristics. The most vital examinations of competing theories, how the comet reacts to maximum solar heating, whether fragmentation transpires, how outgassing distributions evolve, will transpire largely concealed from Earth-based monitoring. When 3I Atlas reemerges from conjunction in late November, investigators will confront the challenge of analyzing observations of a body that may have transformed dramatically during its invisible perihelion transit. The post-conjunction manifestation could either confirm present theoretical frameworks or introduce fresh enigmas that demand entirely distinct explanations. The scientific controversies surrounding 3I Atlas represent the wider challenge of comprehending occurrences that transpire only infrequently and under circumstances that strain observational capacities to their boundaries. Each measurement carries imprecision, each framework makes presumptions, and each interpretation must accommodate the possibility that interstellar bodies operate according to physical principles not yet uncovered through solar system observations. Before exploring the domain of genuinely speculative possibilities, scientific methodology requires that we exhaust the unusual but still reasonable natural accounts for 3I Atlas's perplexing characteristics. The comet may be peculiar beyond present comprehension, but it likely remains within the parameters of established physics, albeit functioning under circumstances so severe that they've never been witnessed before in human observation. The carbon dioxide prevalence identified in 3I Atlas's coma furnishes the initial indication toward comprehending its extraterrestrial character through conventional cometary science. This composition indicates formation in a zone of its natal star system where temperatures remain sufficiently low for CO to solidify into crystalline ice, while water persisted primarily as vapor. Such circumstances typically manifest beyond what astronomers designate the carbon dioxide frost line, the separation from the star where carbon dioxide can crystallize out of the gaseous state. In our solar system, the CO frost line extends much farther from the sun than the zones where most comets originate. This accounts for why solar system comets display water as their principal volatile element, with carbon dioxide assuming only a subordinate function. However, alternative star systems could possess distinct temperature distributions, stellar outputs, or chemical configurations that position the CO frost line at separations where substantial comet formation transpires. A star cooler than our Sun would shift the carbon dioxide frost line nearer to the star, permitting CO-rich comets to originate in the same orbital zones where water-dominated bodies crystallize in our system. Alternatively, a star with distinct chemical composition, perhaps enhanced in carbon relative to oxygen, could generate protoplanetary disks where carbon dioxide formation is preferred over water ice formation, independent of temperature. The formation environment theory accounts for not only 3I Atlas's atypical chemistry, but also its amplified outgassing characteristics. Carbon dioxide sublimes more spontaneously than water ice at identical temperature, potentially generating gas discharge rates that surpass those of water-dominated comets by substantial margins. This enhanced volatility could explain the swift brightening witnessed in September and the extraordinary dimensions of the coma identified by SPHERX. However, the CO-rich composition alone cannot account for the sunward extending anti-tail that has mystified watchers since the initial comprehensive images materialized. This is where dusty plasma mechanics enters the calculation, introducing mechanisms that function at the junction of solid mechanics, gas dynamics, and electromagnetic occurrences. When solar ultraviolet radiation ionizes gases in a comet's coma, it generates a plasma medium of electrically charged particles that responds to both gravitational attractions and electromagnetic fields. This ionized substance interacts with charged dust particles in intricate ways that can generate self-organizing formations unlike anything forecast by straightforward gravitational and radiation pressure frameworks. Charged dust fragments can establish streams, filaments, and even helical formations when affected by magnetic fields transported in the solar wind. Under particular circumstances, these electromagnetic phenomena might overcome radiation force, permitting matter to travel in trajectories that appear to contravene fundamental comet mechanics. The outcome could be anti-tail formations that extend toward the sun while traditional tails stream away from it. The plasma mechanics explanation gains plausibility when evaluating 3I Atlas's amplified outgassing rates. Superior gas concentrations establish more opportunities for ionization and charge transfer mechanisms that could magnify electromagnetic phenomena. The atypical chemical composition might also affect plasma generation through molecular varieties that ionize more spontaneously or at distinct rates than those characteristic of solar system comets. Rotational condition offers another pathway for accounting for 3I Atlas's aberrant characteristics through traditional physics applied to severe circumstances. A nucleus with exceptionally gradual rotation could develop temperature disparities between its illuminated and shadowed hemispheres that focus outgassing in particular zones, rather than distributing it uniformly across the exterior. If 3I Atlas rotates gradually enough that its day side achieves substantially elevated temperatures, then solar system comets encounter thermal expansion and gas force could establish streams of matter expelled with velocities sufficient to overcome solar radiation force in the sunward trajectory. The outcome would be preferential ejection toward the sun from the warmest zones of the nuclear exterior. The gradual rotation theory requires accounting for why 3I Atlas would rotate distinctly from characteristic comets. Interstellar bodies encounter distinct evolutionary mechanisms during their passages between star systems. Impacts with interstellar dust fragments, gravitational exchanges from transiting stars, or magnetic field interactions could all modify rotational conditions in ways that don't transpire for bodies remaining within singular stellar systems. The emerald coloration that manifested in September presents its own natural explanation obstacles. Diatomic carbon characteristically generates green discharge in comet comas, but preliminary spectroscopic measurements displayed comparatively minimal indication for carbon-containing molecules other than carbon dioxide. However, the threshold theory proposes that C discharge became substantial only when 3I Atlas crossed a particular temperature or solar radiation threshold near the 2 astronomical unit separation. This threshold phenomenon could originate from carbon dioxide photodissociation, the decomposition of CO molecules by solar ultraviolet radiation into carbon monoxide and atomic oxygen. Additional photodissociation of carbon monoxide could generate the carbon atoms essential for diatomic carbon formation. The mechanism demands particular radiation circumstances and molecular concentrations that might not have been present during 3I Atlas's preliminary observations, but developed as the comet advanced closer to the sun's vicinity. Alternative carbon chemistry involves intricate organic compounds that could persist in trace quantities within the nucleus, but generate detectable discharge only under particular excitation circumstances. Polycyclic aromatic hydrocarbons, amino acids, or other organic substances could decompose under severe solar radiation to generate carbon-containing fragments that fluoresce at green wavelengths. Surface composition fluctuations offer another natural account for 3I Atlas's atypical characteristics. Rather than a homogeneous nucleus composition, the body might incorporate discrete zones with distinct chemical compositions, some abundant in carbon dioxide, others harboring water ice, and still others containing intricate organic substances. As 3I Atlas approaches the sun and distinct zones of its exterior encounter heating for the initial time, these chemical fluctuations could generate outgassing distributions that transform over time. The preliminary CO dominance might represent early triggering of the most volatile surface reserves, while subsequent heating could reveal subsurface substances with distinct compositions. Porosity and internal architecture also affect comet characteristics in ways that could account for 3I Atlas's aberrant properties. Profoundly porous nucleus, essentially loose assembly of ice and dust held together by feeble attractions could permit deep infiltration of solar heating that triggers subsurface volatile reserves ordinarily insulated from external temperature modifications. The amplified porosity theory accounts for both the substantial coma and the swift brightness transformations. Deeper heating triggers larger volumes of volatile substance than characteristically transpires in more compact comet nuclei, establishing gas generation rates that surpass framework forecasts. Based on surface heating alone, Interstellar processing during 3I Atlas's passage between star systems might have established structural alterations not encountered by solar system bodies. Cosmic ray bombardment, interstellar dust impacts, or thermal cycling during transits through distinct radiation. Contexts could all modify nucleus characteristics in ways that affect characteristics when the body finally encounters severe stellar radiation. Most probable account for 3I Atlases. Exceptional characteristics involves amalgamations of these natural mechanisms functioning simultaneously. CO-rich composition propels amplified outgassing. Plasma mechanics establishes anti-tail formations. Gradual rotation focuses activity in particular zones. And intricate chemistry generates the witnessed color transformations. While each individual mechanism remains within well-comprehended physics, their interaction, under the severe circumstances of an interstellar comet encounter, might generate occurrences that appear unfeasible when evaluated through the perspective of solar system comet. Observation: 3I Atlas could represent a profoundly peculiar comet rather than something fundamentally extraterrestrial. But that peculiarity renders it precisely the category of body that could transform comprehension of small body mechanics. Throughout the galaxy. Now, we explore territory where science fiction intersects with speculative possibility, where the demarcations between natural occurrences and genuinely exceptional explanations begin to dissolve. While no credible indication supports these unusual interpretations of 3I Atlas's characteristics, the comet's unprecedented properties invite the category of speculation that has accompanied every unexplained astronomical occurrence throughout human chronology. These concepts exist not as serious scientific theories, but as thought experiments that illuminate precisely how peculiar our interstellar visitor truly is. The extraterrestrial technology beacon theory represents arguably the most persistent unusual account for atypical astronomical bodies. Ever since Oumuamua's discovery ignited controversies about artificial origins, each fresh interstellar visitor inevitably produces speculation about potential technological indicators. 3I Atlas's swift brightening, atypical anti-tail formation, an amplified coma could theoretically represent triggering sequences of some configuration of automated probe engineered to react to stellar radiation contexts. The beacon scenario envisions 3I Atlas as a dormant technological artifact that remained inactive during its prolonged passage between star systems, conserving power and structural integrity until encountering circumstances that initiate predetermined activation protocols. The brightening occurrence in September could mark the instant when solar radiation achieved adequate strength to energize dormant mechanisms, while the anti-tail formation might represent directed energy discharges or material expulsions serving some technological objective. However, this technological interpretation confronts immediate obstacles when challenged with observational indication. The spectroscopic indicators identified by James Webb Space Telescope and ground-based observatories display distinct indication for standard volatile substances, carbon dioxide, water vapor, and organic compounds that correspond to anticipations for natural comet outgassing. No atypical isotopic proportions, artificial substances, or energy indicators characteristic of advanced technology have been identified. The quasi-living plasma theory ventures even further into speculative domain, drawing on investigation into intricate plasma characteristics that can demonstrate seemingly organized distributions under particular circumstances. Laboratory experiments have verified that dusty plasma mixtures of charged particles and microscopic solid particles can self-organize into formations that demonstrate characteristics reminiscent of biological systems. These plasma configurations can reproduce, evolve, and react to environmental modifications in ways that superficially resemble living organisms. Some investigators have theorized that such intricate plasma arrangements might emerge spontaneously in space contexts, potentially developing characteristics that mimic primitive life configurations. 3I Atlas's atypical outgassing distributions, anti-tail formations, and reactive brightening could theoretically represent manifestations of such plasma-based occurrences. The living plasma notion suggests that interstellar space might harbor configurations of organization that function according to physical principles, completely distinct from carbon-based biology. These theoretical entities might remain dormant during interstellar transit, but become operational when encountering the electromagnetic context surrounding stars, generating observable phenomena that mimic but don't genuinely represent biological mechanisms. Yet this account demands invoking physical processes that remain purely theoretical. While dusty plasmas can indeed establish intricate formations under laboratory circumstances, scaling these occurrences to comet-sized bodies functioning in the solar wind context demands extrapolations far beyond present scientific comprehension. No observational indication suggests that 3I Atlas demonstrates the category of electromagnetic indicators anticipated from large-scale plasma organization. The deliberate scout narrative transforms 3I Atlas into an active reconnaissance operation from another star system, complete with programmed characteristics engineered to examine our solar system during its transit through the inner zones. This scenario envisions the comet's atypical properties as intentional features. The substantial coma might furnish sensor capacity or communication range, while the anti-tail formation could represent data transmission arrangements aimed at distant receivers. Scout theory suggests that 3I Atlas's brightening represents not random outgassing but regulated triggering of observation and communication mechanisms as the body approaches its principal mission objectives. The timing of peak activity near Mars and during perihelion could represent predetermined survey protocols rather than straightforward responses to solar heating. This interpretation leads to romantic speculation about 3I Atlas awakening as it encounters the radiation signature of our star system, its artificial consciousness emerging after millions of years of dormant interstellar transit. The emerald coloration might mark the instant when dormant sensors commence functioning, while the swift brightness transformations could signify data processing and transmission operations. However, the Scout scenario confronts the identical evidentiary obstacles as the technological beacon theory. The chemical indicators, thermal characteristics, and structural properties of 3I Atlas all correspond to anticipations for natural bodies, albeit atypical ones. No indication suggests information processing, directed communications, or other operations characteristic of technological arrangements. The exotic matter theory proposes that 3I Atlas harbors substances or functions according to physical principles unfamiliar to present science. Theoretical physics suggests possibilities for unusual configurations of matter with atypical characteristics, dark matter interactions, modified gravitational characteristics, or quantum phenomena functioning on macroscopic scales that could generate observable occurrences. Unlike anything in standard physics, exotic matter could potentially account for 3I Atlases, a typical anti-tail through gravitational aberrations that redirect matter flow, or explain its amplified outgassing through energy discharge processes beyond traditional chemistry. The swift brightening might represent exotic phase transitions, or energy storage arrangements that function according to physics yet to be uncovered. This account permits natural occurrences that nonetheless surpass present scientific comprehension, suggesting that 3I Atlas represents not artificial technology, but natural mechanisms involving physics that human science hasn't yet encountered. The body could serve as an inadvertent laboratory for examining physical principles that don't manifest under circumstances characteristic of Earth-based investigation. The temporal aberration. Speculation explores the most unusual territory, suggesting that 3I Atlas might represent some configuration of information or matter transfer across cosmic timescales. Science fiction scenarios envision the comet as a message or artifact from our own future, transmitted backward through time using technologies that circumvent traditional causality constraints. This interpretation treats 3I Atlas's atypical characteristics as indication for temporal manipulation rather than spatial transit between star systems. The body might originate from a future iteration of our own solar system, transporting information or substances intended for our present era. Its peculiar characteristics could represent interactions between future technology and present-day physical circumstances. However, temporal manipulation scenarios demand physics that not only remains undemonstrated but contradicts fundamental principles of causality and thermodynamics as presently comprehended. No observational indication suggests that 3I Atlas violates conservation principles or demonstrates temporal aberrations beyond the normal relativistic phenomena anticipated for high-velocity bodies. The analytical perspective on all these unusual accounts emphasizes how frequently apparently mysterious astronomical occurrences receive mundane accounts once adequate data becomes accessible. Pulsar discoveries initially produced speculation about artificial transmissions from advanced civilizations, but these bodies proved to be rapidly rotating neutron stars. Fast radio bursts ignited similar controversies before being traced to natural astrophysical mechanisms. History suggests that 3I Atlas will ultimately discover explanation within established physics, albeit perhaps involving mechanisms or circumstances not previously witnessed. The comet's atypical properties likely represent the severe diversity of circumstances present in alternative star systems rather than manifestations of unusual physics or artificial technology. The merit of investigating these speculative scenarios resides not in their probability, but in their capacity to emphasize precisely how exceptional 3I Atlas genuinely is within the framework of human astronomical observation. A body that can seriously inspire considerations of extraterrestrial technology, living plasma, and exotic matter represents something genuinely unprecedented in our comprehension of interstellar visitors. As 3I Atlas continues its concealed transit through perihelion, these unusual accounts serve as reminders of how extensively we still don't comprehend about the universe beyond our solar system. Whether the comet emerges from conjunction as a thoroughly mundane, if atypical body, or continues displaying properties that challenge traditional accounts, it has already succeeded in expanding the parameters of what we consider feasible for visitors from alternative star systems. Cosmic chronometer advances toward a succession of instants that will determine not only what 3I Atlas discloses about itself, but what it instructs us about the wider population of bodies wandering between the stars. Each approaching milestone represents a vital examination of our comprehension, our observational capacities, and our capability to extract meaningful science from occurrences that strain every boundary of present astronomical practice. October 3, 2025. marks the initial vital juncture 3I Atlas's nearest approach to Mars at approximately 30 million kilometers. This encounter represents humanity's optimal opportunity to maintain surveillance of the interstellar visitor during the interval when Earth-based telescopes commence losing visual contact with it. The mechanical instruments orbiting Mars will attempt observations never envisioned by their original mission architectures, extending technological capacities to capture images and spectral data from an object hurtling past at velocities characteristic of interstellar travel. The outcome hinges on factors outside human influence. Should C-2023A3 Sokinshan Atlas sustain or amplify its present luminosity, the Mars-orbiting spacecraft could potentially acquire comprehensive imagery of its nuclear architecture and coma behavior that terrestrial telescopes cannot discern. Conversely, should the comet diminish from its September zenith, even the most sophisticated spacecraft sensors may register only faint signals, inadequate for substantive scientific interpretation. The latter part of October ushers in the concealed culmination, perihelion occurring between October 29th and 30th at roughly 1.36 astronomical units from the Sun's center. Throughout these pivotal days, C-2023A3 will endure radiation intensities capable of triggering the most profound metamorphosis of its entire solar system transit. Peak thermal exposure may energize volatile materials that have persisted in stable states throughout the comet's interstellar voyage, potentially generating outgassing phenomena sufficiently spectacular to modify the object's essential properties. However, perihelion transpires almost precisely when C-2023A3 becomes most challenging to monitor from Earth, obscured within solar brilliance that no terrestrial telescope can pierce. This celestial paradox positions the instant of greatest scientific significance exactly where human observational capacity reaches its lowest threshold. Whatever phenomena perihelion produces will remain predominantly concealed from direct surveillance, retained only in whatever circumstantial data endures for subsequent examination. The observational deficit persists through early November, establishing a 4 to 5 week interval during which C-2023A3 essentially disappears from human surveillance. This enforced blackout transpires during what theoretical projections indicate should constitute the comet's most volatile phase, potentially encompassing fragmentation occurrences, substantial luminosity fluctuations, or chemical alterations that would ordinarily prompt intensive observational initiatives. Reappearance in early December constitutes the subsequent critical juncture when solar separation increases adequately for Earth-based telescopes to reacquire and monitor C-2023A3 following its obscured transit. The comet that resurfaces from conjunction may demonstrate scant similarity to the object that vanished in October, potentially exhibiting indications of fragmentation, radically modified brightness, or transformed chemical makeup reflecting its confrontation with severe solar heating. The post-perihelion schedule prolongs the scientific prospects through the succeeding year and further. The Jupiter flyby in March 2026, while transpiring at substantially greater distance than the Mars encounter, may furnish supplementary spacecraft observation possibilities as C-2023A3 commences its ultimate departure from our solar system. The spatial arrangement could permit remote observations by missions such as Juno or the forthcoming Europa Clipper, contingent upon their operational condition, and orbital arrangements. The knowledge potentially gained from successful observations transcends the particular attributes of C-2023A3 itself. Interstellar chemical analysis delivers direct specimens of substances synthesized near other stars, retaining information regarding chemical circumstances present in protoplanetary disks across the galaxy. The carbon dioxide dominant composition already identified suggests formation conditions dissimilar to our indigenous solar nebula, implying that planetary system chemistry exhibits greater variability than previously conceived. Cometary behavior investigations under extreme circumstances could transform comprehension of volatile discharge mechanics, dust particle dynamics, and plasma physics in extraterrestrial settings. The anti-tail manifestation contests fundamental suppositions about how cometary materials react to solar radiation, potentially necessitating novel theoretical constructs that accommodate electromagnetic phenomena not incorporated in conventional models. The scientific ramifications extend to broader inquiries concerning interstellar objects and their function in chemical development throughout the galaxy. C-2023-A3 constitutes merely the third confirmed visitor from beyond our stellar neighborhood. Yet its anomalous characteristics indicate that the galaxy contains far greater diversity in small body formation than existing theories anticipate. Each interstellar object examined furnishes essential reference points for comprehending how prevalent such visitors may be and what they disclose about circumstances in remote stellar systems. Fragmentation examination. Should C-2023-A3 experience disintegration during perihelion, could deliver unprecedented understanding of interstellar object internal architecture and compositional stratification. Distinct fragments might harbor materials from various strata within the primordial nucleus, effectively supplying cross-sections of an object formed around a foreign star. The fragment distribution configurations and chemical disparities could unveil structural particulars impossible to ascertain from intact object. Observations. Tempering expectations necessitates recognizing the constraints inherent in studying objects that persist at the threshold of perceptibility, even under ideal circumstances. C-2023-A3 will presumably never transform into a naked eye phenomenon for Earth-based observers, with maximum brightness projections hovering near magnitude 11 to 12 well within telescopic capability, yet invisible without optical assistance. The absence of a dramatic visual exhibition doesn't compromise the scientific merit, though it does constrain public engagement opportunities that frequently stimulate continued investment and attention in astronomical investigation. The European Space Agency's perspective. Comet interceptor mission, slated for launch in the late 2020s, represents one endeavor to cultivate rapid deployment capabilities for examining newly identified interstellar objects. Unlike conventional spacecraft missions that demand years of preparation for designated targets, Comet Interceptor will remain stationed in space at the Earth-Sun L2 Lagrange point until an appropriate target manifests, then redirect to intercept and investigate the object during its solar system passage. Nevertheless, Comet Interceptor's capabilities remain constrained by the fundamental obstacle of detecting interstellar objects sufficiently early to permit spacecraft intercept operations. C-2023-A3 was identified only months preceding its nearest solar approach, affording insufficient time for dedicated spacecraft missions, even if such rapid deployment capabilities existed. Future detection infrastructure must recognize interstellar visitors years beforehand to enable meaningful spacecraft encounters. Ground-based survey enhancements present more immediate prospects for advancing interstellar object science. The Vera C. Rubin Observatory, presently under construction in Chile, will initiate operations in the mid-2020s with unprecedented sky survey capabilities. Its capacity to systematically image extensive portions of the celestial sphere could identify interstellar objects considerably earlier in their solar system passages, furnishing extended observation intervals and superior opportunities for comprehensive study. The Legacy Survey of Space and Time Rubin Observatory's principal mission anticipates discovering interstellar objects at a frequency of several annually, once complete operations commence. This substantial increase in detection rate will metamorphose interstellar object studies from infrequent, opportunistic observations to methodical population, surveys that can address fundamental questions regarding galactic small body repositories and their chemical evolution. Technological advancements in adaptive optics, spectroscopy, and space-based observations persistently expand the boundaries of what can be ascertained from faint, rapidly transiting targets like C-2023A3, next-generation extremely large telescopes. Incorporating the 30-meter telescope and the European Extremely Large Telescope will furnish light-collecting capacity and spatial resolution that could revolutionize interstellar object characterization. The James Webb Space Telescope's infrared proficiencies have already validated their significance for interstellar object studies, supplying chemical composition intelligence impossible to secure with previous instrumentation. Future space-based observatories optimized for small body investigations could deliver continuous monitoring capabilities unaffected by Earth's atmospheric constraints or solar conjunction intervals. International collaboration becomes progressively vital as interstellar object studies necessitate synchronized observations across multiple installations and time zones. The C-2023A3 Observing campaign has illustrated both the promise and the complications of orchestrating global response to rapidly developing astronomical targets. Lessons derived from this coordination endeavor will guide future responses to comparable discoveries. Data distribution and analysis methodologies developed for C-2023A3 observations are instituting standards for how the astronomical community manages rapidly evolving high-priority targets that demand immediate response from multiple observational facilities. These methodologies will prove indispensable as interstellar object discovery frequencies escalate and opportunities for coordinated study become more routine. The wider implications reach beyond astronomy to fundamental questions regarding the constitution of matter and chemistry throughout the galaxy. C-2023A3 furnishes direct physical testimony about conditions in other star systems, conserved in pristine condition during millions of years of interstellar transit. Each measurement contributes to understanding how planetary formation mechanisms vary across divergent stellar environments. Astrobiological considerations emerge from interstellar object studies, as these visitors might convey organic compounds or even rudimentary life forms between star systems. While no evidence proposes that C-2023A3 contains biological materials, its organic chemistry could furnish insights into the dispersal of complex carbon compounds throughout the galaxy. The identification of amino acids, nucleic acid bases, or other prebiotic compounds in interstellar objects would carry profound implications for understanding how life's chemical constituents propagate through space. C-2023A3's distinctive chemistry, while not directly biological, demonstrates that interstellar objects can maintain complex molecular architectures across galactic distances. Planetary defense considerations, though irrelevant to 3I Atlas, given its safe flight path, gain valuable insights from interstellar object research that enhances our comprehension of how such bodies react to solar radiation. Potential future interstellar arrivals may follow paths that bring them in closer proximity to Earth, necessitating precise predictions of their dynamics for impact hazard evaluation. The distinctive features of 3I Atlas underscore the shortcomings in existing models employed to forecast comet activity, indicating that planetary defense infrastructure must accommodate object categories that diverge from solar system norms. Improved comprehension of interstellar object mechanics could become essential for precisely evaluating dangers from forthcoming Visitors that may present authentic hazards. Public outreach prospects surrounding 3I Atlas demonstrate both the obstacles and advantages of conveying advanced scientific research to mainstream audiences. The comet's technical intricacy and dim appearance create impediments to widespread public fascination. Nevertheless, its interstellar heritage and anomalous characteristics generate enthusiasm among those who grasp its importance. Academic institutions across the globe are integrating 3I Atlas observations into educational programming, employing the comet as a live demonstration of scientific exploration and advancement. Students can monitor the observation initiatives, examine publicly accessible information, and observe how scientific knowledge develops as fresh evidence materializes. The commercial aerospace sector displays growing attention toward small celestial body research, acknowledging both scientific merit and prospective economic prospects in asteroid and comet analysis. While 3I Atlas offers no extraction or resource gathering possibilities due to its hyperbolic path, the methodologies refined for examining it enhance broader competencies for characterizing small bodies that may prove commercially beneficial. As we approach the pivotal October timeframe, 3I Atlas has already proven successful in establishing that interstellar travelers will repeatedly challenge our preconceptions about what exists in the universe beyond our solar neighborhood. Whether the comet's subsequent activity validates existing hypotheses or introduces entirely fresh enigmas, it has set a new benchmark for the unforeseen in celestial occurrences. The ultimate defining statement that will shape 3I Atlas's legacy hinges on what observations disclosed during the critical weeks approaching. 3I Atlas is beginning to unveil what it genuinely represents: a chemical archive from the molecular cloud of another stellar system, a physics laboratory functioning under circumstances never previously witnessed, or perhaps something even more remarkable that will compel us to revise our conception of what traverses the interstellar void. Within the coming weeks, it will either ignite into extraordinary luminosity, disintegrate into a shower of interstellar fragments, or glide silently past our sun, transporting its mysteries back into the cosmic darkness. Whatever transpires could fundamentally alter how we conceptualize visitors from distant suns. The directive for anyone equipped to pursue this cosmic investigation is unambiguous. Monitor for mission imagery releases from ESA's Mars Express and Trace Gas Orbiter, NASA's Mars Reconnaissance Orbiter, and MAVEN. Then anticipate the post-perihelion reports from Hubble Space Telescope and James Webb Space Telescope that may ultimately disclose what 3I Atlas authentically embodies. The cosmos has dispatched a herald from another star, and we are about to discover what communication it conveys.